Okay, welcome everyone to session 6 of our Sage Days. We have 4 talks here. This session is branded the Symbolic System Symposium. We start with a talk about computation in geometry. That's a talk by Yuan Zhou, University of Kentucky, on solid angles of polyhedral cones via decompositions and power series.
I'm Yuan Zhou from University of Kentucky, and this is a joint work with my PhD student, Alison Peterson. We are working on solid angle of polyhedral cone. So the talk structures as follows. First, we will define a cone and solid angle measure on the cone. I will show you some application. Also, I will try to sell you our Sage math implementation of the solid angle measure. We will see that in lower dimension, like dimension 2 and 3, this solid angle is well defined and there exist straightforward trigonometry similars. But beyond dimension 3, the formula gets much more complicated. The known formula is through power series. However, it does not always converge, so there is a condition attached to it. Not every cone satisfies that condition. Therefore, we developed a method for cone decomposition that allows us to compute the solid angle of any simplicial cone in any dimension. Finally, if time allows, I will talk about the error bound, symptotic analysis of how our computation behaves. Okay, I'm sure most of you know the definition, but nevertheless, let's go through the definitions for cones. A convex cone is a subset of Rn such that it is closed under conic combination. That is, if I take 2 points, x and y, in this cone C, and I scale them, then combine them, then the new point is still in C. This is the definition of convex cone. A special case is the polyhedral cone. A polyhedral cone C is finitely generated. There are 2 ways to generate a polyhedral cone, either by giving a finite number of half spaces, and then the polyhedral cone is just the intersection of these finite family of half spaces. Usually this is called the edge representation of a polyhedral cone. The other way is to give a finite number of generators. Say we have vectors v1 through vm, then the conic combination of them defines a polyhedral cone C. C is the conic hull of finite many vectors. This way of definition usually is called the V representation. So I have some figures here. The first example, I have 2 vectors, or you can think about as 2 rays, but in this case, it is, according to some people's definition, it is a cone, but I want to point it out, it's not a convex cone, not a polyhedral cone, because it is not convex. The second feature, the ice cream cone, it is a convex cone. It is closed under conic combination. However, it is not a polyhedral cone because it is not finitely generated. The third feature, a plane in the 3D space, it is a convex cone and polyhedral cone. It can be thought as the intersection of the upper half space and the lower half space. So finitely many half spaces, their intersection define this plane. It can also be thought as the cone generated by 4 vectors. Well, x positive direction x, negative direction x, positive, negative directions in y. So another way to define it. In the case, it's a polyhedral cone. The last example is also a polyhedral cone. It's pointed, meaning that it does not contain a line, and a set of vector generators are drawn in blue. Okay. Please stop me at any moment if there is something unclear or if you have a question. Sage has the class cone, and also it has class the polyhedral. Both of them can do computations with cones. Let's try to see an example. Say we have 4 vectors, a set of vectors v, v1, v2, v3, v4. Then a cone C can be defined as, well, just give the cone such vector generators. Then C is a cone in 3D. Let's try to visualize C by plotting it. Yesterday, we learned about from William and his team about Cocal, about Jupyter Notebook, Sage Notebook. I'm still new to it. I have yet to improve my presentation for the moment. Let's stick with the low-tech technology, the basic Sage session, and plot it. We see this is the visualization of cone C in 3D. We can ask for the edge presentation and B representation by calling C.facets or C.rays. Try that. I mentioned that another way to the constructed cone is using the polyhedral class. Actually, we can convert a cone to a polyhedron, and then P is 3-dimensional polyhedron. Visualize P. P.plot. Also, we can ask for the facets and the generators rays. Okay. In fact, these two, well, this polyhedron, sorry, they can be directly constructed using the polyhedron class by providing the rays. And you can test that the two are the same. Okay. Now, a couple of more definitions. The dimension of a polyhedral cone C is the dimension of the smallest affine space containing C. For instance, we have this C, we can ask for its dimension by calling dimension method. And a crucial definition, simplicial cone. A polyhedral cone C is simplicial if it has a linearly independent system of generators. So a polyhedral simplicial cone is pointed, and if it is in dimension D, then it has exactly D linearly independent generators. In Sage, we can test if a cone is simplicial by calling is simplicial. We see that the example we have of cone generated by 4 linearly independent vectors in 3D, this one, C, is not simplicial as expected. Okay. What can we do if a cone is not simplicial? Well, we can decompose it into simplicial subcones. Let's do that. Simplicial subcone decomposition of V. Recall that V is the set of generators of C. And let's see what the simplicial decomposition does. It decomposes the cone C into 2 cones. It gives 2 sets of generators. Using them, we get 2 cones. And again, we can visualize each of them. C0 is actually a part of C. Then we overlay this with the second cone in the generator, in the decomposition. Now we see the cone C with 4 generators is decomposed into 2 simplicial cones. Okay. On this slide, I have the first subfigure is the VC, is the cone C we talked about. Then the other 2, they are simplicial, noticing that the last figure is a 2D cone in 3D space, it is generated by two vectors. The affine space is 2, so it has a linear independent system, so it is simplification. Now it's time to get to the main object, solid angle. Let's first define it in arbitrary dimension Rn. Actually, roughly speaking, the solid angle of cone is the ratio of the space that the cone takes. Formally, there are two ways. Well, one is through the intersection with a ball, one is through the intersection with the sphere. Let's give them a look. So C is a cone with the apex at the origin. We intersect C. C lives in space Rn. We intersect it with a unit ball, compute the volume of the intersection, and take the ratio of it with respect to the volume of the unit ball. This step is to normalize so that the whole space, the cone that takes the whole space, has solid angle 1. Similarly, we can define solid angle through the intersection of a sphere. Sn-1 is the unit sphere lives in Rn, is the S-1 sphere. Its intersection with the solid cone is a subset of the sphere, compute its volume, and take the ratio of it with respect to the volume of the total sphere. It gives the solid angle, normalized solid angle measure. All right. That's the definition in arbitrary dimension. Now, let's reduce the dimension to a very easy case, R2. In this case, the solid angle is just the angle between the two generating vectors. And this can be computed easily by trigonometry simula. Actually, you know, the dot product of two vectors is defined as the norm, the product of their norm times the cosine of the angle. So through the inverse mapping gives the solid angle in terms of the dot product. An example is shown on the slide. We see that the cone takes, well, half of the first order, so 1/8 of the half the whole space. Therefore, the solid angle in R2 of this cone is 1/4, and this agrees with the formula of the arc cosine. Okay, just to notice there is a normalization factor 1/2 pi. Okay. Now go to 3D. The solid angle is also well defined, and we also know a closed formula by the trigonometry function. The normalized solid angle measure of the cone generated by the unit vectors V1, V2, V3 is the ratio of the area of the spherical angle triangle formed by the unit vectors to the surface area of the unit sphere. It's not too hard to show that the solid angle measure in 3D, normalized 3D solid angle, follows the formula. Okay. So solid angle in 2D, 3D exist, closed formula via trigonometry, and beyond 3D, I'm not aware of such closed form formulas, but it's an interesting topic for a number of reasons. Well, in the literature, I learned that people care about solid angle because of 1, 2, 3 here. One can compute the number of simplices in a triangulation of an n cube. One can calculate the PPI score, which is related to solid angle, and to compute the volume of the feasible domain of an ecological community. For my application, well, my motivation application, because I work in linear programming, if you take a course on linear integer programming, you know the standard method is a branch and bound, meaning that you will have to iteratively add many cutting planes to solve the IP. And there are a bunch of cutting planes, different ones, and to decide which ones are important, which ones are strong, or which combinations of certain cutting planes would theoretically lead to a good result. We hope that the solid angle measure could shed some light on that. Okay. Now I'm trying to sell you our Sage mask implication of solid angle. We have the code implemented and uploaded to GitHub. It has the implementation of 2D, 3D trigonometry similar, and beyond that, for 3D, the power series similar, power series formula, and the decomposition method. We are trying to merge step by step to Sage math. So my student Allison has the following tickets: implementation of solid angle measure for the special case of two-dimensional simplicial cone. Then the next step is two-dimensional cone. Then the trigonometry formula for 3D and beyond. Okay. Let's take a look what they do. For example, the 2D formula. This is the diff. Maybe it's best to look at the documentation. So first it has a simplicial subcone decomposition method. We showed an example a moment ago. Then it has a method to compute solid angle in 2D and also for simplicial cone as a special case. Instead of going through the documentation, I will just show you some easy examples. So start by 2D, sorry. Solid angle of, okay, let's take two vectors, unit vector, normal basis, 0, 1, 1, 0. We expect this to return 1/2 because it's the first ortho. Let's see, yes. Without the simplicial, well, solid angle 2D as a general 2D method should also be able to compute that. Yes, it does. Okay, now we have two vectors. They are, this gives a minimal description. What if we insert a vector inside the cone, in the interior cone? That is, we do not give a minimal description of the solid of the cone. Well, our code, what it does is it does the simplicial subcone decomposition to decompose it to two simplicial cones and compute their solid angles and add them up. This avoids asking for double description method to return the minimal description of a cone. It doesn't matter in 2D, maybe it helps, the decomposition method helps in higher dimension. Now, let's give it an example that is not simplicial. For instance, a half space in 2D. What can we do? Well, first ortho, then a negative vector. This is a half space. Its solid angle in 2D should be 1/2. And indeed. Let's try high dimension, 3D. We know the formula exists. Well, it's through arc tangent. We had the example there about, yeah, this is the V. Let's try if we can compute the solid angle of this non-simplicial cone in 3D. We call solid angle 3D. Yes, it does something and it returns the result. Hopefully it's correct. Okay. So we are merging our implementation into Sage step by step. I showed you an example in 3D, but haven't told you how it was computed. Actually, there was a known formula through hypergeometric series. It's a special case of power series. Let's see, how am I able to annotate on the slides? don't see the option here. All right, I will just say it then. So in a normal standard power series, you take like summation over index from 0 to n, coefficient a sub k times x to the k. X is the variable. Now we change it a little bit, change the variable to multivariable. We change x to alpha. Alpha is a multivariable. It contains n choose 2 components. Say we have a cone C lives in Rn. It is simplicial, so it is generated by n minus 1 n vectors. We take the pairwise dot product of its generators. Thus, we have a multivariable alpha containing n times n minus 1 over 2 variables components. Similarly, if we change the variable to multi-dimension, we also need to change the exponent used to be k. Now it's a. A has the same dimension as alpha, so n choose 2. And this last term denotes for alpha raised to a. The coefficient, well, we said the multi-exponent is taken over a, used to be k from n, now is a from n raised to n choose 2. N is the set of natural numbers. The coefficient here used to be ak, now maybe it's denoted as a sub a, so it's a function of a. In this function, we have this part, the gamma here is the usual gamma function. So this formula gives a hypergeometric series. It is a special case of the power series where two neighboring coefficients, a sub a and a sub a plus 1, their ratio is a rational function of a. In that case, we call it a hypergeometric series. Anyway, we have this hypergeometric series, and the theorem states that under some nice conditions, which we don't care for a moment, under some nice conditions, this series converges absolutely to the solid angle measure we want to compute. How to prove this? It's a bit complicated. Maybe I can give a rough idea of why it holds. So we know the solid angle is defined by the ratio of volume. And then the equivalent way is that we take the ratio as ratio of volume as ratio of integration. We take a function f that is invariant under rotations. And in particular, we choose a very nice function. E of u is exponential of minus u absolute value at square. This has the property that by choosing this f, the denominator will be exactly pi raised to n over 2. Then we just need to take care of the denominator, which by a change of coordinates, we can write it in this form. And by some lemma, the exponential term here can be written as in terms of the alpha raised to a. Alpha is the dot product matrix. And also using a standard a known result of the integral relating to gamma function, it's not very hard to compute, well, the solid angle formula in terms of this power series. Okay. More interestingly, let's show the code. Okay, we have this again on the GitHub repository, not yet implemented to Sage, but will soon be there. Let's take a matrix which gives the vectors, generating vectors, generate the cone by providing its generating rays. I start by an example in 3D, although I claim this formula works for higher dimension. I start by 3D because I can plot it. Let's do it. It is a very acute cone. The method is called solid angle general that uses the power series to compute solid angle. It gives a result. We know for 3D case, there was the trigonometry formula called 3D angle, solid angle 3D. So let's compare if the two formulas give roughly the same result. Let's see if the error between them is very small. Actually, it is. Okay, we are satisfied. This is an example in 3D. We can do it in higher dimension as well, as long as that mystery nice condition holds. Let's see an example in 5 dimensions. Again, I give 5 vectors in R5 and ask Sage to compute solid angle through power series. Yes, it gives. Notice that the power series is infinite, and for the computation, we truncate it to a fixed multi-degree. Here I specify it is 10. Last example, I specify it is 20. So necessarily there is an error, and in the last part of my talk, I try to bound that error. Okay. So the examples I showed you, we were able to use the power series to compute solid angle. That is because we were lucky. The mystery condition here, something related to the positive definite associated matrix, this condition holds for the previous examples. And what is that condition and exactly? Well, let's define associated matrix. We have a cone in Rn generated by n unit vectors. The associated matrix is just like V transpose V. But for the entries of the diagonal, we flip the sign. Actually, we take the negative of the absolute value of the entry values. So on the diagonal, it's always 1 because we start by unit vectors. V transpose V has all 1 entries on the diagonal, and off the diagonal, there are negative entries. The theorem says if this associated matrix is positive definite, then we are fine. Then the power series converges absolutely to the solid angle measure. However, this condition does not hold always. Let's see an example. We have this C, looks like a simple cone plotted. This one. It is a simplicial cone. However, its associated matrix is not positive definite, as predicted by is n alpha positive definite? No. What can we do? If we call directly solid angle general, then it will throw a warning or error message saying that the associated matrix is not positive definite, thus the series is not convergent. So what we do, we decompose. Before showing you the theorem and how it works, the details, let's look at an example. Let's stick with this C. We have the other file on the GitHub here called decompose. And in that file, we have the method generate cones decomposition. And sorry. Also, the main method is called solid angle measure. What it does is it decomposes the given cone into cones, into subcones. Each of the subcones satisfies that positive definite associated matrix condition. Thus, we can compute its solid angle through the Power series formula. Then we do a plus minus combination and get the final result. Let's try it. Solid angle measure on that cone C. Truncated at multi-degree 30, it gives a result. Again, this is a 3D example. Let's compare this result with what the trigonometry formula gives. Actually, we see they're not very far. There is another way to truncate our computation. Here we fix the degree, the sum of degree, and we can also do it by specifying a error range epsilon. Not exactly in that spirit. So when the two consecutive terms in the power series, they are very small, smaller than the epsilon, we stop computing. And we see the result it obtains is quite good. Okay. Let's go back to the slides. Now it's time to study how we decompose a cone that does not satisfy that nice positive definite condition into subcones. The main idea is we borrow it from the so-called Brian-Vecnier decomposition with respect to line. Suppose we have n vectors, they are linearly independent, form a basis for Rn, and we have a cone generated by such vectors. Now we have another vector. It can be written in the basis BW. So another vector mu. We are trying to decompose the cone C along the vector mu. The fourth theorem says we can decompose the cone C into, well, roughly n parts. Each one is generated by all the other W's, but Wi, we replace Wi by this specific direction vector mu. Noticing that in the generators, the vectors Wi and mu can be positive or negative. The signs are indicated by epsilon I and delta I. Also in the decomposition, the cones can be plus or minus. So this sign is predicted by SI. And you may notice here, it is not equal to, but equivalent to or equal to up to a modulo. And here the modulo stands for modulo the indicator functions of cone containing lines. The bracket notation here is the indicator function, and the 3 bars here is modulo cones containing lines. I will give an example of this. I will explain this example in a moment. So we have the formulas to decide how to choose the signs and how to choose which summand index I should take. I skip. Okay, for this particular example, the cone was generated by V1, V2. They form a basis. Now, the specific direction is mu -1, -1. For the first cone, in the decomposition, we replace V1 by plus or minus the mu. So we have this blue cone. And the second component in the decomposition, we replace V2 by something related to mu, actually minus mu. So we have the second cone. The sign says, well, blue minus yellow should be equal to the green modulo something. Let's see what that modulo means. Well, if you take the difference between these two, it is not yet exactly the original cone. Actually, the difference between these two subcones in the decomposition is minus of this purple thing. And here the modulo thing comes into play. It is to modulo the cone containing lines. Namely, in this example, we consider the half space, upper half space. We add to the difference, the half space, then we obtain the original cone. How does this decomposition with the modulo thing help us in computing solid angle? Well, if we can satisfy, if we can claim that for each of the subcone, we are able to use the power series to compute its solid angle, then this cone containing lines should not pose a challenge, because we can project it to a lower dimension. If we are able to compute all cones, solid angle of all cones in lower dimension, and then we have a lemma to lift it to cones in higher dimension containing lines. Okay, so this is the first way to understand it. I will explain another way via dualization, which get rid of this cone containing lines plus or minus in the decomposition. Okay, that's the theorem, the main theorem of cone decomposition. We are given a couple of vectors. They form a simplicial cone in Rn. We claim that this cone can be decomposed into n-1 factorial cones. Each of them has the nice property that, well, generators are unit. The last generator Cn agrees with Vn. The first n generators form the same space, and there is a perpendicular orthogonal property of Cn with respect to all the first n-1 vectors. And most importantly, after rewriting it, well, after decomposing it, for each subcone, we have this nice formula saying that basically the associated matrix of the cone J is positive definite. Therefore, we are able to compute the solid angle of the subcone J. And then using the sign from the Bryan-Bechnier decomposition, we are able to get the solid angle of the original cone. I'm not going to bother you with the detailed proof, but the sketch is like, well, we start by a cone C with generating vectors v1, vm. Because of that theorem, we choose a special vector mu. Here we choose it to be the last vector bm. So actually we first dualize it, consider its dual cone, then decompose its dual cone. In that decomposition, there is a modular. The modulo is with respect to cones containing lines in its dual space. Now dualize back to the primal space, we get a decomposition of the cone C. Here is another modulo, but this modulo is with respect to the dual of cones with lines in the dual space. They are lower dimensional cones in the primal space. Therefore, lower dimensional cones have solid angle 0. So they do not play, well, they do not affect the solid angle computation. And by doing one round, we fix Vm and get some nice orthogonal property of Vm with respect to the previous vectors. And then we do induction on the proof, decompose the first n-1 vector space so that finally we can get this property, positive definite associated matrix. And this somehow explains where the factorial n-1 factorial comes from. Coming back to our example, we saw that this cone is, well, does not have a positive definite associated matrix. But now with this decomposition, we can add a blue cone to it to get, well, the purple one is equal to the red one minus the green one. Here, the modulo is with respect to a lower dimensional space, that specifically the intersection of the two cones, that is the face here. So a lower dimensional face has solid angle 0, therefore we have this formula. For blue and red subcones, we are able to compute solid angles via power series because their associated matrix are positive definite, and therefore we get the result here. And this is exactly what this computation does. Okay, I have 5 minutes. Actually, so we now know how to compute solid angle in arbitrary dimension. Somewhat. But there are some caveat here. Well, the power series formula is taking sum over indices living in n raised to n choose 2, and choose 2 is quite large. And if we want the computation to be fast, probably we want to reduce the number of non-zero terms in the multivariant alpha in the dot product. That is, we want to make the cone generators, well, the vectors to be, many of them to be orthogonal. A possible way, well, here is an example in 3D. We had to choose from ABC from n to the 3. If somehow we know one of x, y, z is 0, then we only need to choose AB over n to square, and that saves us time. One way to do it in general is we want many zeros in V transpose V in the dot product, and it's same to say we want many zeros in the associated matrix. And a quite extreme case is we want the associated matrix to be tridiagonal. Actually, it has all ones on diagonal and only non-zero entries just above and below the diagonal lines. In this case, instead of choosing indices from n, choosing n over choose 2, n times n minus 1 over 2 indices, we just need to care about n minus 1 indices, be beta 1 through beta n. The good news is our decomposition theorem we just talked about, following the same decomposition and the same induction proof, we were able to get all the subcones in the decomposition having that diagonal associated matrix form. So that's nice. Finally, well, we have to truncate the series computation at some point. We showed truncating it at error and truncating it at degree, but we need to figure out a way. And it would be nice if we have error bound analysis. That is what we do next. So say with using the multi-degree as a truncating criterion, and we define the error. So A sub B is the coefficient in the power series. Let's see, we truncate this at n1, n2 through n minus 1. We do it for the tridiagonal case. So we have n minus 1 variables and minus 1 coefficients. Let's study the terms associated with exponent beyond n1 through n minus 1. So one of the exponent B, well, used to be A in the tridiagonal case, because there are only n minus 1, we call it B1 through Bn minus 1. Let's look at the terms in the power series whose B, one of their BI's is greater than the given NI. And the sum of those terms, absolute value of those terms. We are trying to bound that error, that sum. We claim that, well, this is something related to the minimum eigenvalue of the tridiagonal associated matrix. Already we knew from Ribanto's formula that the power series converges only if the associated matrix is positive definite. So the minimum eigenvalue plays a role here. Now we show that the tridiagonal error bound, if we truncate as at well, n1 through n minus 1, or we do a few L terms further, then the error is decaying in an exponential way. I skipped the details, but the highlights are, well, the error is somehow related to the minimum eigenvalue of the tridiagonal associative matrix. We can expect an exponential relation for the errors. And if we know at some point at multi-degree N1, N2, we know the term. We also have the exponential decay, then we can find an exponent so that error is as small as we like. Future directions. Well, we know how to compose cone into subcones that we can compute their power series, and by combining them, we get a formula or computation method for solid cone of simplicial cone in arbitrary dimension. What we do not know is if there is a simpler formula, if there exists a closed form formula, just as in lower dimension 2D, 3D, does that exist? We talked about positive definite associative matrix, and we wonder what are the conditions that give such nice positive definite associative matrix with conditions in terms of the original matrix, original V, matrix V. We may spend time on analyzing the computational complexity. We may want to reduce the number of cones in the decomposition. Our theorem showed it's upper bounded by n-1 factorial, but can we make it smaller, or can we make it a very special? And there are ongoing work for error estimate for the power theory methods. And of course, we want to apply this to our motivation example of cutting planes in integer programming. Okay, that's all I want to say. Thank you for your attention. And if you have questions, please do not hesitate.
Thanks very much. Next speaker is Fredrik Johansson. Please.
So thank you very much. It's always nice to be at the Sage Days, even if it's just a virtual one this time. So the idea is that I will speak a bit about FLINT, just a bit of an introduction about FLINT and some related projects for people who may not be familiar with these libraries. And then I will talk a bit about what's going on with FLINT, latest features, and the development plans for the near future. And we can probably have some discussion towards the end also about issues with interfacing with FLINT from Sage and Python. And this is all intended to be very informal, so feel free to interrupt me at any time if there's something you want to ask or discuss. So what is FLINT? FLINT is a library that is used in Sage and other places. One of the things it does is that it provides very fast polynomial arithmetic. So if you create polynomials over the integers in Sage, for example, it will use FLINT behind the scenes, and you can create some large polynomials, let's say with degree 10,000 and pretty big coefficients. And FLINT will multiply these polynomials in a fraction of a second. So in fact here, the output would take 80 million characters to write down. And actually, if you do this conversion to a string, it takes almost as long time to convert to a string as to multiply it. FLINT does polynomial arithmetic. It also does a lot of other things that I will talk a bit more about in a few moments. So just to show what FLINT looks like, if you actually use the C library, if you use the C API, you would typically create objects of some FLINT types like FMPZ poly. It's the integer polynomial type that Sage wrapped on the previous slide. So the interface, it's very similar to GMP. You have mutable objects, you have to initialize them, and then you call methods to manipulate the objects. So this is just performing the same calculation as on the previous slide, just a bit more verbose to do it in C, but it will also be a bit more efficient. In this case, when you're doing some operations on really huge polynomials, the overhead of working from Python will not really be important, but if you're doing something with a lot of small polynomials, then you might want to do something in C or from Sage, maybe in Python. So FLINT does a lot of different things. It provides implementations of arithmetic over a few different base rings. So there's integers, there's rational numbers, there's integers mod n, finite fields, and p-adic numbers. And we have different implementations for different sizes of n and different sizes of finite fields with different optimizations. And then over most of these base rings, we have other structures like matrices. We have both univariate and multivariate polynomials. Then, of course, since FLINT is a number theory library, we have things like integer factorization and primality proving, which uses a lot of the usual algorithms. FLINT is not as fast as some of the more specialized software for factoring or proving primality, but it's on par with or typically a bit faster than ParyGP, for example. We also have a lot of different number theoretic functions, special functions. For matrices, we have a lot of standard exact linear algebra like solving and factorizations and normal forms over the integers, lattice reduction, and so on. For polynomials, we have a lot of special functions and functions for manipulating power series also. There's, at least for now, no dedicated types in FLINT for power series. Instead, you would just use the polynomial types with power series functions. For polynomials, and perhaps this is most interesting for multivariate polynomials, we implement some non-trivial functionality like multivariate GCD and factorization. FLINT doesn't do Gröbner bases, which is a bit for political reasons, but also because doing Gröbner bases really efficiently, it's a huge project that no one really tried to work on within the scope of the FLINT project so far. And a very important principle of FLINT is that we use asymptotically fast algorithms when possible. So we have typically asymptotically fast multiplication algorithms and then different ways to reduce other operations to multiplying so that we can really take advantage of that. So the design of FLINT, it's written in plain C, and it's supposed to be developer friendly, so it's well tested and documented. We don't have a dedicated public or private API. Instead, we try to keep everything documented and accessible to make it easy to work on FLINT. We rely on GMP and MPFR for basic arithmetic. And then we implement a lot of algorithms optimizing for different cases, both for large and small operands. FLINT is multi-threaded, so it can take advantage of multiple cores. And it's pretty large right now, about 600,000 600,000 lines of code, which can be seen as a good thing or as a bad thing, depending on what aspect you're looking at. I think one of the questions people ask most often about FLINT is its relation to GMP. Why FLINT provides its own integer type FMPZ instead of just using the GMP MPZ type. And it's basically a question of performance. So the FMPZ type in FLINT, it's for a small integer, it's just a single word. So a small value up to 2 to the 62 will be stored directly in this word, and otherwise the FMPZ will become a pointer to an MPZ allocated on the heap. So this is much faster in general than using the GMP MPZ type, which always allocates memory on the heap. So the idea is that most of the time your integers will not be very large. So then for small values, you will just have one word, and you can do arithmetic operations in just a few cycles. Now, on top of this, we rely on GMP for most of the high precision integer arithmetic. And then on top of GMP, we add a lot of functions that would not really be in scope of GMP, because GMP is almost a system library. It's used by compilers and cryptographic software and a lot of other applications that don't need state-of-the-art number theory functionality. And then also for performance, FLINT has its own FFT code, in fact, that is a bit faster than GMP for big multiplications. And unlike GMP, which is single-threaded, FLINT can also take advantage of multiple cores. So in fact, I have a fun slide with some timings that Daniel Schultz, one of the FLINT developers, did recently. So this is a timing of how long it takes to multiply two n-bit integers, and the time is normalized by n log n. So theoretically, you would expect that the performance would be constant, at least as n tends to infinity. So the black plot here, it's how much time it takes with GMP. So here it's using classical multiplication and Karatsuba, and at this point it's switching to the FFT. And the red plot here, it's the FLINT FFT. So you can see it's a tiny bit faster than GMP asymptotically. And the brown one, it's FLINT with 8 threads. So you can see that with multiple cores, you get a pretty big speed up over GMP. And then you may wonder about the mysterious other things here, the blue and purple curves. And I don't think I should say too much about this because it's maybe still a bit of a secret, but it's maybe some new FFT code that potentially will be in a future version of FLINT that is even faster on one core. So in fact, many times faster than GMP on one core and even faster on multiple cores. But that will not be a topic of this talk. It's just something that may turn up in the future. So very briefly about some of the related projects. So there are a group of C libraries that are not part of FLINT itself, but kind of grew out of the FLINT project and add more functionality on top of FLINT. And the first one is Antic by Bill Hart, which basically does algebraic number fields very efficiently, very efficient arithmetic in algebraic number fields. There is my library ARB, which does real and complex Bol arithmetic. So it allows you to do arithmetic with real and complex numbers with rigorous error bounds. And then on top of this, it provides a lot of different functions like special functions. And it has some tools for things like numerical integration, and also some utility functions that maybe could be located in FLINT instead, like code for Dirichlet characters, but it's currently part of ARB. And more recently, I also started working on a library called Calcium, which provides exact real and complex numbers. And you can have both algebraic numbers and transcendental numbers. And I will not say too much about that either right now. It's something we can discuss later a bit about interfacing with Calcium in Sage, because I think it could be interesting for many applications. But essentially, it's using a combination of exact arithmetic. So it's using algebraic number fields from Antic, and it's using multivariate polynomial arithmetic from FLINT, and combining that with ARB for rigorous numerics, and trying to put things together so that you get a kind of abstraction for exact real and complex numbers, which doesn't always work perfectly. I mean, there are situations where this is not a good computational model of real and complex numbers, but there are times where it works really well, like I think for many symbolic applications. And Calcium also provides some more utility functions that maybe could be in FLINT. I will talk a little bit about the new upcoming version of FLINT, 2.9. We put out a beta release a couple of weeks ago and a first release candidate today. So if you have the possibility, it would be nice if you can test it, and if there are any bugs, report them as soon as possible before we make the final release. So what I have here is some of the features in 2.9. It's not the biggest feature release we have ever made, but there are some nice features, some optimizations to integer arithmetic, and to mod n arithmetic, which I think the biggest speed up here will be for linear algebra with small matrices, will be quite a bit faster. There are some optimizations to finite fields. We have some new functions, like functions for nth derivatives of polynomials and Eulerian polynomials, some optimizations of Stirling and Bell numbers. We added more square root functions for different rings. I don't remember what this refers to. I think it's square root power series functions for power series over finite fields and other rings maybe. And maybe square root functions over finite fields also. There's functions for solving for singular matrices or non-square matrices over the rational numbers. Previously, we only had functions for solving non-singular square systems over Q. So that's just a small convenience feature. We added support for multivariate polynomials with 0 variables. I don't know how useful that is, but I guess it makes the interface a bit more useful. we have FFT matrix multiplication for faster multiplication of matrices with really large entries. And we added some more helpers for parallel programming, which I will get back to a bit later. So not the biggest feature release of FLINT ever, but I think some nice new features. So the people who contributed to this version, to this release, are Bill Hart, who has been the lead developer of FLINT since 2007, me and Daniel Schultz, and Albin Albeck. So Bill and Daniel are currently at the University of Kaiserslautern, where they are working on FLINT with funding provided through the Oscar project, which some of you may be familiar with. And Albin is, I believe, a master's student in Gothenburg. So he's been helping out a bit with FLINT maintenance and with some new functions and performance patches. So a big, I should also say that there are many more people who have helped out with testing and minor bug fixes and so on. A big thing that's happening with FLINT this year is that you can see I wrote until 2022 for both Bill and Daniel, because they are both planning to step down from the project in the near future. Bill, after this release of FLINT, will step down as maintainer, and Daniel will also step down from FLINT development later this year. So Daniel's plan is to move, he's from the United States, so he plans to move back to the United States. And just a small advertisement is that he's currently looking for a job, or he will be looking for a job in the United States. So if you have a use for a really good programmer with a solid mathematical background, you should definitely get in touch with Daniel. Or if you know someone else who might be interested, you should definitely get in touch. So these are the 4 main contributors to this version of FLINT. Just to emphasize that FLINT is a huge project that has been in development for a long time, and a lot of people have helped out. This is just some of the names, and several people here are well known in the Sage community, and I think I saw at least Alex Best in the participant list. Several of these were Google Summer of Code students, and others just contributed to FLINT as part of their research, or in some cases just out of interest. We have a much longer list of contributors on the FLINT website. So in terms of the future of the FLINT project, with both Bill and Dan planning to leave in the near future, our plan right now is that I will take over maintenance of FLINT and will be responsible for development. And I'm interested in ideas for finding new sources of funding to maybe get some more staff involved in the FLINT project. In the past, it was really a huge help to have the support of Open Dream Kit and then the Oscar project. And we've had other grants as well. And myself, I tried to apply for some small grants for ARB and Calcium, but I didn't have much success with that so far. Google Summer of code students have been very helpful in the past. I guess the only thing that's a bit sad is that none really continued working on FLINT after the project was finished, but maybe you can't really expect that. I think the problem is that you also need good mentors for Google Summer of Code, and at least in my case, I stopped mentoring because it was simply too much time. I might have time sometime in the future again, but if people want to be involved in the FLINT project, being a Google Summer of Code mentor could be a good way. Another idea is to get staff through my employer, INRIA. They can potentially provide research engineers to help out with usually with specific scientific tasks. Like if there is some scientific goal, you can get some engineering support to achieve that. I don't know how useful or practical this is, but it's maybe a possibility to look at. I will also mention that also the future of MPFR is a bit uncertain. There are only 2 active developers, Paul Zimmerman and Vincent Lefebvre, and it's really Paul who's responsible for the mathematical side of MPFR, and he's retiring in a few years. And after that, it's not really clear who will take over. And Paul actually asked me if I would be interested in maintaining MPFR, but I said that, well, I'm responsible for FLINT. It's probably a bit too much for me to do, even if it would be quite interesting to do. So, yeah, if you have ideas for research projects that could involve developing FLINT, or ways to find funding, or if you're interested in helping out with FLINT development in any way, then I hope you will get in touch.
Do you work on software full time, or do you have another? Do you have in this in addition, or what? I'm just curious.
Yeah, so I'm employed as a researcher, which in practice means so for INRIA in practice means that I can do anything I want. I should still write some papers. I think the higher ups will be happy if I produce some papers. And I think I will be happier too when I write some papers occasionally. But yeah, I spend a good portion of my time just developing software. Probably the majority of my time. So for the rest of the talk, I will talk a bit about my plans for the future of FLINT and related projects. So there are several things that I plan to work on. Of course, there's performance optimization, which is not necessarily the most urgent thing to work on, because I think for most things, FLINT is already fast enough, but it's fun to do, and it could always be useful to someone. So there's, on one hand, just simply coming up with better algorithms and improving the implementations. And then there's also an important thing is to optimize for modern hardware, taking advantage of multiple cores and new instruction sets. Of course, adding more functionality. I think it's also a bit of a necessity to try to clean up FLINT a bit, maybe find ways to reduce the code size, decrease bloat a little bit, because it will, well, it will make FLINT more convenient to develop, and it will be faster to load, to download and install and so on. So I think that's just a good thing if we can make it a bit more lean. I have thought about ways to consolidate all these projects, FLINT and ARB and so on, maybe even merging them. Mainly because right now it's a bit of a hassle that I often find myself with some cool new features at a low level in FLINT that I want to use in ARB. And then it's a bit of an issue because I will work against the Git repository of FLINT, and then people use the Git version of ARB, but they don't have the latest Git version of FLINT, or there's a new beta version of FLINT, and ARB no longer works with that beta version because some function name was not updated and so on. So it could be, I'm thinking about ways to simplify development, essentially. Another idea that I will show in a few slides is adding generics, so generic structures to FLINT itself. And then, of course, interfaces are an important topic as well. So just a few more words about multi-threading. So FLINT has been thread safe for a long time. It's an important design aspect. And we have a lot of multi-threaded algorithms internally in FLINT now. Polynomial multiplication, most notably, but also a lot of other things. But there's always more things that can be made multi-threaded. So it's mainly a question of finding interesting functions that people rely on and then trying to find ways to make them parallel in an efficient way. So I should note that FLINT actually just uses one thread by default. You have to call the function FLINT set num threads if you want FLINT to use a certain number of threads. And I think Sage doesn't wrap this function right now. So if it's something someone wants to hack together quickly, it should. I think you could do it with 2 lines of C types. If you want to do it very easily, just call FLINT set num threads. And well, you could try then multiplying 2 really large polynomials and see if it makes a difference. So one of the new things in the 2.9 release that I mentioned is some new parallel programming helpers that you can use internally in FLINT and in libraries that use FLINT to simplify parallel programming. So it's just 2 C functions, and the first one, it just executes a bunch of independent things in parallel. Like can be useful, for example, if you want to do a computation mod p for several different primes. And the second one does binary splitting. So it does a divide and conquer operation where it evaluates a lot of different values of a function and then combines them using binary splitting, so in a tree. So that's useful for a lot of asymptotically fast algorithms that are used on the based on the binary splitting paradigm. So one of the things I've been doing the last couple of weeks in ARB is to use these FLINT helper functions to speed up different functions. So for example, numerical integration in ARB is now multi-threaded. So as an example, if you evaluate this integral to 1,000 digits, it would take on my laptop 2.4 seconds on 1 core. If you enable 8 threads, then it only takes 0.4 seconds, so 6 times faster. So that means it's using 8 cores, both for first for generating the Gauss-Legendre nodes and weights for integration, and then it also evaluates the function values in parallel, basically. So it's very easy operation to parallelize. Then there are some more functions like Bernoulli numbers. You can compute the millionth Bernoulli number now in less than 5 seconds. And exponential function. So I'm working on parallelizing things like pi and elementary functions, so that at very high precision, they also use multiple cores. So this is basically based on parallel binary splitting. There are also some other things that are parallel internally. So typically, there are a few different things to do internally. So it's not completely trivial here. But I found that it was not really difficult to get a pretty good parallel speed up. So I think in the near future, I will continue doing this because it's pretty easy and you get pretty nice results very easily. Another thing that people very frequently ask about, especially about ARB, is how to take advantage of vectorization, either just using SIMD instructions on CPUs or even better using GPUs. And the short answer is that you can't really do it with the kind of arbitrary precision types you have in FLINT and ARB, like FLINT multi-precision integers or ARB arbitrary precision real numbers, because it's really important for vectorization to work with fixed width data. Otherwise, you will not really get good performance. So yeah, a lot of people have asked about accelerating ARB and FLINT with GPU support, especially. And I think basically for that, you need to convert to different representations internally. And it's actually something that FLINT already does in some cases, like for matrix multiplication. Like if you have a matrix over the integers, it will first reduce it to multiplying several smaller matrices mod p, and then it will either do it using the CPU, using integers, using integer instructions, or it can even use floating point, so it can use the BLAS, which will be even more efficient on modern CPUs, which have vector operations, so they can do several floating point operations at the same time. So FLINT already does this in some cases, but it's something that we could do much more extensively, also in ARB. And I should also mention that NTL uses this kind of approach. It uses vectorized modular arithmetic internally, and it's quite a bit faster than FLINT for some things right now. Victor Schuck did some benchmarking here where he shows that NTL wins over FLINT a lot of the time for some operations. There are other operations where FLINT is faster, so it really depends what you are doing. A more specific idea for ARB that would be interesting to look at, it's doing ball arithmetic with machine precision or with a double arithmetic. So you would have a ball with 106 bits of midpoint and 53 bits of radius. And that's something that you should be able to parallelize quite well with vectorization or on a GPU. So these are some interesting things to look at. Could be interesting to look at in the future. It could be interesting research projects or student projects for very good students. Personally, I have other plans for the near future. So I don't think I will be working much on this towards this in the next year or so, but in the longer term, it could be interesting. I think it's really important in the long term because it's really the direction that hardware is going, that GPUs are getting faster and vector instructions are getting faster, but just the normal integer units, the serial integer units on processors are not improving that much. Another feature I'm working on right now, what I do plan to work on probably for much of the next year, it's an implementation of generic rings directly in C. So this is, I have a separate Git repository for this right now, but once it's stable, I might put it in FLINT itself. And the idea is just to let you create rings using something very similar to Sage with parent objects and then elements, where elements can be basically any C type or FLINT type or any type that the user constructs. So you could have, this is showing some code where you could create a context object which defines a parent, so defining the integers. So you initialize this context object with init fmpz, and it tells you that the elements of this ring will be FLINT fmpzs. And then you create a context object representing polynomials of integers. And then the interface for working with this, it's a lot like the interface in FLINT for specific types. Now, the advantage of this is that it's completely recursive. So you could create polynomials over polynomials over polynomials. And also, it's completely uniform for all the FLINT types. That's the idea that right now, when you have different FLINT types and you want to interface with them, you have subtle differences in the interfaces. But with generics, you could actually have the same, exactly the same interface for all types. So it would be a bit easier to interface with FLINT potentially using this.
Could you say something about why that doesn't exist already? Like,
yeah, that's a very good question. So from the beginning, FLINT had just a few types. It had integers and polynomials over integers and rational numbers, and well, we started adding more and more types, but we kept sticking to the design that we just made a completely separate type for each mathematical domain, which in a way makes sense because when you want to make things efficient in practice, you really need completely different algorithms in many cases for the different types. So the algorithm you use to multiply polynomials over the rational numbers is not at all the same that you use for multiplying polynomials with integers mod n, for example. As things progressed, of course, we have been more and more, well, it becomes more and more of a limitation not having generics. You end up with more and more duplicated code and ad hoc generics. In practice, we already have several special purpose implementations of generics in FLINT. There's template-based generics for well, C header file template generics for finite fields. There's already some pointer-based generics for evaluating multivariate polynomials. And then there's union-based generics for the FQ default types that gives you a single interface to all the different implementations of finite fields, and so on. So in practice, we already have a lot of special purpose generics in FLINT. So part of my idea is that maybe if I do something a bit more systematic, it could maybe replace some of those. So it would be a bit nicer. Another reason is that, well, when Bill Hart started really thinking about this problem several years ago, his conclusion was that you really need a better programming language. C is simply not good enough for doing computer algebra at a high level. You really want memory managed language with a lot of convenience features that you don't have in C. So he started working on his own programming language for this, actually. But then Julia came along, so he started working on Nemo for Julia instead. He decided that he thought that Julia will probably be, it was not perfect, but probably will be good enough. And now you have Nemo, which is kind of doing generics. Well, it's two packages for now. It's Nemo and abstract algebra, but together they provide a wrapper of FLINT, and then on top of that, also generics. So what I'm trying to do here will certainly be much more limited in scope. I don't think it will be a complete system for doing computer algebra. It will more be something that could be useful within FLINT for generic algorithms, being able to apply generic algorithms to multiple types, and for interfacing with FLINT. So one of the things that I highlighted here is that you have different special cases with things like ARB rings that are not exact. Then you have calculum rings where things like testing if something is 0 will not always succeed. So there are all kinds of error handling and subtleties that you have to deal with if you want something generic that works with all these different types. So I'm trying to do that correctly. And it's maybe something that could be useful for Sage and other projects as well, because there are, in practice, a lot of bugs when you take generic code in Sage and apply it to something inexact. Like there will be probably some algorithms in Sage designed for exact elements, and when you use them with balls, then things don't always work correctly. So it's something that I'm trying to get right from the start with this C-level generics. So it's still a bit of an experiment. I'm not 100% certain that it will work out, but it looks promising so far. I will work on this in the next months, and hopefully I will have some more progress to share in the near future. So I will move on to the last topic I wanted to discuss, which is interfacing with FLINT and with these other libraries. So there are several ways to do this right now. If you want to use FLINT from Python, you have the FLINT wrappers in Sage, which are very incomplete. They only wrap some of the types in FLINT and ARB and some other functions. And they are, well, more designed around using FLINT for specific things that are useful in Sage and for really exposing all the features available in FLINT. And this is using the Sage object model. So you have, so if you want to create a FLINT integer polynomial, it will be, it will have a parent that will be a Sage parent and so on. So there's another wrapper for FLINT called Python FLINT, which I've developed. So it's standalone. It doesn't involve Sage in any way, and it's the interface. It's a bit more of a direct analog of the C-level interface. You have an FMPZ polytype for polynomials that doesn't require a parent object. So that can be more convenient or more easy to work with. It can also be a bit less, well, it depends on what you're doing. Which kind of interface is more convenient, I guess. This interface, it's a bit more complete, but doesn't cover everything in Flint and ARB. And it needs a bit of maintenance for building everywhere, for convenient distribution and so on. And I guess a question we can discuss is whether there should really be two separate wrappers. Maybe it would be possible to have one low-level wrapper to Flint and ARB and so on. And then Sage objects that build on top of this. I don't know if it's practical or if it's better, but it's something that we can discuss maybe. Then, of course, there is Nemo in Julia, which is certainly the most complete interface and also the most efficient, because Julia is a lot more efficient than Python. But I don't know how useful this really is to the Sage community. In principle, I believe you can call Julia from Python, but of course, Julia is a huge dependency, and it's probably not the way most people who use Python want to interact with Flint, using Julia as an intermediate. And yeah, as I mentioned before, the C generics that I'm working on right now could potentially be helpful, because instead of having dozens of types and hundreds of functions to wrap for each type, with some differences between all the types, you will just have a single interface for all the types. So potentially it could make interfacing a lot easier. So I had nothing else planned to say, but I'm happy to answer questions and discuss.
Well, first of all, thanks a lot. And we do have a few minutes of time for questions.
So is the C++ interface with Flint being maintained? I know that originally it was just one project, but does it include all of Flint?
No. So the C++ wrapper in Flint was written by a Google Summer of Code student, Tom Bachman. And it was, I'm not too familiar with the C++ interface myself. I believe it was using state-of-the-art C++ features at the time, but which are now a bit out of date, and it's really difficult to maintain, unfortunately. And I think no one has really been interested in this. So in practice, I think it compiles, it works, but it hasn't been updated, so it doesn't cover new functionality. So I think a nice project, if someone is interested in this, would be to simply do a new C++, do a completely new C++ wrapper for Flint using modern C++. It should allow keeping things more simple and easier to maintain.
I have a question that you might not want to answer, but I'm curious if you could share any philosophical thoughts about C versus other languages for the sort of problems and things that you're building here? Just because, you know, Bill, as you mentioned before, ended up going down that rabbit hole.
Yeah.
And I've had many discussions with him, but you know, obviously you have a huge amount of experience and ability with C. And I'm just curious what you think, if you can share any thoughts at all. And, you know.
Yeah, C is a horrible language in many ways. It has some aspects that are really nice for this kind of work still. It's very obvious what code does, at least if you code things in a reasonable way. I mean, it's very explicit. C code is very verbose and explicit. And it can be a good thing for this kind of code because you can really understand what's going on. So you can understand the performance characteristics at a very detailed level. Yeah, then there are things like the fact that C is pretty stable. I mean, compilers like to break things. New versions of compilers like to complain about things that is actually perfectly fine. They like to add new warnings, things like that. But on the whole, it's very stable. So that's also a good thing.
So
for
can you hear me?
Yeah.
I can add one thing to this discussion. We're seriously missing exceptions in FLINT.
Yeah, I agree.
We cannot deal with exceptional circumstances because of the restrictions of C.
Yeah, that's one of the major limitations of C. For a really high level programming, the kind of thing, the kind of language you'd really want to use for implementing a computer algebra system at a high level. Well, I have a lot of things to say about that, but we don't have time right now. So just
there will be more time after, so at the end of this whole session for discussion on things where even full-length rants about programming languages are not exactly encouraged, but if necessary, can be endured. So there will be plenty of time to discuss. Okay, so yeah, we still have time for quick questions.
So Fredrik, can you hear me?
Yes.
Yeah. So you mentioned the idea, I saw it on the mailing list as well, about merging some combination of these libraries together, and which obviously from your perspective, it makes it easier as the maintainer of all of them, which you apparently will be now. Yeah, from my perspective, kind of thinking downstream from that, that's also quite convenient if everything's in one big library that we can just bundle together. But I wonder if the kind of the big problem at the moment is about getting maintainers and getting more people to help with maintenance. I wonder whether I think whether that makes it worse or better, basically.
I don't see merging things making things worse. I think there's
I mean, if we think to a future where, you know, hopefully we're not just depending, you know, on, there are more people who are helping to maintain these things.
Yeah.
So if say you needed to go and do something else, then does it make it easier or harder for someone else to step in and?
You mean in terms of the fact that there would be more code to maintain?
Well, in general, it's just, you know, maintaining a smaller library is easier than maintaining a large one, right?
Yeah, sure. I would say that these 4 libraries that I mentioned, they are reasonably consistent. They have very similar code conventions, the same build system and testing and so on. It's all done, documentation, it's all done pretty much the same way. So in that sense, it's already kind of just separate directories of a big project from my point of view. So yeah, I don't see that it would be that it would have many downsides. I think the big one that people have suggested that I should keep ARB as a separate project because that way I will get more credit personally, but I don't think it's really an important reason, a good reason.
Maybe not, but I think it is true. I mean, there are colleagues of mine who know of you through ARB,
Yeah.
but not through anything else.
Yeah. Well, at the same time, I sometimes talk about ARB with people, and people tell me, but it's a bit annoying that ARB depends on FLINT. Can't you just throw away this dependency on FLINT? But it's a bit ridiculous because ARB would not really make much sense without FLINT. It builds very, very heavily on top of the fast basic arithmetic that FLINT provides.
Okay, so let's thank Fredrik again. And as I said, there will be more opportunities for open discussion later on.
Thank you.
And we continue with a presentation by the SymPy team.
I'm Aaron here. I work at Quantsite, and Oscar Benjamin. I don't know if you want to introduce yourself.
Hi, I'm Oscar. I was just talking a moment ago. I'm from the University of Bristol in the UK.
Yeah, and so we're going to be talking about SymPy today. And I guess, yeah, Oscar, if at any point you want to jump in, feel free to just let me know. SymPy is it's a pure Python BSD licensed computer algebra system. It is one of the many libraries that is included with Sage. So it started in 2005, and it's had over 1,000 people contribute since then. It's a very popular library with almost 2 million monthly downloads between PyPI and Conda, and 9,000 stars on GitHub. And you can see that there's on GitHub, there's 41,000 repositories and 1,200 packages that depend on SymPy. Just here's some basic examples of what SymPy looks like and some of the features, which I'll be going over a little bit more later. But you can see here, we import SymPy, define a symbol. Here we have a symbolic integration of this function here. This example here is showing two things, actually, that it can solve this equation, and it produces this set that represents the solution of this equation. And also this is showing the pretty printing, which it can do in the terminal. So the output looks nice. There's code generations, so turning expressions into code. I'll be going over that a bit more later. And also showing the interface between other Python libraries using the lambdify function, which I'll also be going over. So here we're turning this expression, sine x times cosine x, into a function that can be evaluated using NumPy. So the full feature list of SymPy, it's pretty extensive. Pretty much anything that falls into the realm of symbolic computation it has as a feature. So basic expression manipulation, polynomials, standard symbolic integration, differentiation, equation solving, number theory, discrete math, matrices, geometry, plotting, predicate logic, set theory, group theory, statistics, cryptography, parsing. We have functions to parse LaTeX, C, and Fortran. Pretty printing, like I showed earlier. There's several modules for different areas of physics, including mechanics and quantum physics, differential geometry, and code generation. So where is SymPy used? It's used in many places. People use it for education, for finance. People use it in various machine learning applications. One of probably the biggest use is just virtually every scientific discipline can make use of symbolic computation as a modeling tool to help sort of use the computer to derive whatever mathematical equations are needed for that particular problem. A very common workflow there is to make use of the code generation and other interfaces to take the symbolic expressions that are generated by SymPy and convert those into things that can be numerically evaluated. And in addition to that, it's also a dependency of quite a few Python libraries as well. So as I mentioned, it is included in Sage. I'm actually not entirely sure exactly which parts of Sage interface with SymPy and which parts maybe use SymPy by default or not. I think someone else here might have to comment on that. I don't know if you have any, if you know about that, Oscar, but also some of the other libraries are PyDI, which I'll show a little bit more of later. It's a library for doing multi-body dynamics, to uses SymPy to generate symbolic equations of motion. SymPy.jl is a Julia interface to SymPy. It's quite popular. The Octave symbolic library is a wrapper around SymPy. And then just some other examples here. Geometric algebra, this volumetric data analysis library called YT, Circ, which is a library for quantum circuits. There's a library for chemistry. Just to give an idea that the extent of different scientific disciplines that make use of it. There's also, as I showed in that earlier slide, according to GitHub, approximately over 1,000 libraries depend on SymPy. So the basic design of SymPy, it's all pure Python. So everything is Python. There's one hard dependency, which is MP-Math, which we use for numerics. There are several optional dependencies. We can, for example, if you install Gimpy2, it'll use that to get faster integers. You can also do similar things with Picosat, and we're hoping to interface with FLINT in the future. There's also other things like for our plotting module makes use of matplotlib, and we have interfaces with NumPy and SciPy to do numerics. So the basic design philosophy of SymPy is that it is made to be used interactively, but it's also designed to be used as a library for these dependent libraries and make it easy for them to just depend on SymPy as a library. So it's very easy to install. You can just pip install it. All of the classes are designed to be extensible, so it's very easy to define your own symbolic expressions. And it also has very good interfaces with these other libraries like NumPy and so on. Our focus is only on symbolics. So anything that's numeric, we kind of just leave to other libraries. We think of SymPy as the symbolic component of a larger scientific Python ecosystem. So if you want to just do pure numerics, you should look at a library like NumPy or SciPy. Maybe using SymPy to maybe derive the equations and interface with that, but the actual algorithms themselves are not going to be in SymPy. In SymPy, all objects are Python classes, and we just use the Python's operator overloading to do basically to create expressions. Python lets you basically create a DSL for mathematics with its operating overloading. Our philosophy is that we try to follow Python conventions as closely as possible, so that if you're familiar with Python and you're coming from other Python libraries, it's very easy to jump in and use SymPy, because it's going to use the same sort of standard conventions. So for example, we don't override, we don't try to change Python syntax in any way. Like you can see here, we have 3 times x. We don't attempt to make like 3x without this times operator work, because that would be invalid syntax. We use the star for exponentiation, because that's sort of the Python operator. And this caret, we use it for XOR. Symbols must be explicitly defined, just as you would in any other Python code. All variables have to be defined. And of course, we use standard PEP8 naming conventions. The expressions basically form a tree. For example, this expression here will look like this. This 3x plus 1 will be an addition of a multiplication of 3, this integer 3 and the symbol x, and then the add will have this integer 1. And then this dot args attribute will appear on any expression, and that will sort of that'll let you pull these expressions apart. And so most symbolic algorithms are more or less just manipulating this expression tree structure at a very high level. All expressions are immutable. So, oops, and I didn't finish my bullet point on my slide there. So just ignore that. Yeah, immutability basically makes for a much cleaner design. You don't have to worry about hidden state and other sorts of issues that can come with immutability. Whenever a function does something to an expression, it always returns a new expression, and the original is unchanged. So you don't have to worry about things like something else changing an expression from underneath you. And then there's a common, so all the expressions use a class structure, where basically to create an expression object, to create a new type of expression object, like a new function or something, you would just make a new subclass of this basic class. So some of the strong points for SymPy is most of the work on SymPy has been focused on practical applications for people who use it in these other scientific domains. So most of the functionality that's well developed is sort of aiming to facilitate those applications. It's, like I said, it's easy to use as a library. So there use quite a few dependent packages, and it's very easy to just import SymPy and use it or extend it. And also we try to interface very nicely with other libraries. There are some submodules in particular that are well developed. For example, our polynomials, our symbolic integration, I'll mention a bit about later, our set theory, code generation. There's of course always more work to do, but SymPy is being used to solve real world problems today. So I think it's fair to call it a real full-featured computer algebra system at this point. By the way, just as with the previous talk, if anyone wants to interrupt with a question at any time, feel free to. So just to go over a few selected features in a little bit more detail, the code generation, as I mentioned, is a very important feature for quite a few practical applications. So the basic workflow with code generation is you start with some mathematical function, and SymPy represents that function symbolically. And then once you have that symbolic representation, you take that and convert it into code for some lower level language like C. And this it could produce either just an expression, which you would then maybe take that expression and put it in your own code, or it can produce an entire compilable program, or it can even take that compilable program and compile it and give you a function that you can call from within Python, which is what this ufunctify function will do. So here are some of the supported, or well, all of the supported languages that SymPy supports. So most of the sort of common lower level languages that you might want to convert something into to do faster numerics are supported, and the design is made so it's very easy to extend to other languages. So for example, some of the big ones here are C, Fortran, Julia, Python itself via NumPy and SciPy, and yeah, all the other ones here on the screen. So the sort of the basic idea behind code generation is that even if your end goal is to just do some numeric calculations, SymPy is very useful at modeling the problem, and symbolics sort of help you avoid making mistakes. There are instances where symbolic expressions are basically necessary because the expressions you're dealing with may be thousands of lines long if you were to write them out by hand. And also SymPy opens the possibility of actually doing symbolic simplifications, which are things that a traditional compiler would not know how to do. So just to give an example here, this is generated using the PyDI library that I mentioned earlier, and also the SymPy physics mechanics submodule. So if you have this inverted pendulum, which is just this little block here moving back and forth with a pendulum on top of it, if you have one link, the equations of motion are going to look like this. If you change this one link to 3 links, like is in this picture, the equations of motion look like this. So, and you can see that obviously scaling this up to even more links is going to get even more complicated. So this is obviously something that it's basically going to be impossible to do by hand. You can see here's some more realistic examples that you might do with PyDI, and you can imagine the number of the complexity of each of these examples. The equations of motion are going to be basically something that you will have to do with a computer if you want to generate them. Another feature I could talk about is our symbolic integration. We have several algorithms implemented. We have a heuristic Risch algorithm, which sort of the lesser version of the full Risch algorithm. So the Risch algorithm, for those who don't know, is sort of a complete algorithm for integrating elementary functions symbolically. We have partially implemented this Risch algorithm, only the exponential and log cases. There's a manual integration, it's called module, which sort of does integration sort of the way that you would do it by hand, which is useful because it can create step-by-step solutions to integrals that are actually useful to someone like a calculus student who actually wants to understand how the integral should be computed. We have an algorithm implemented that uses the Meurer G function to compute a very large class of integrals using special functions. You can see an example of this below here. So this first example is this complicated function is being integrated using the Risch algorithm. The second example is using the Meurer G function algorithm to compute this definite integral. And then we are currently working on porting Ruby, which is a library written on top of Mathematica that computes a very large class of integrals using pattern matching. So we're currently working on porting those that large pattern matching rule set into SymPy. And when that's completed, that will significantly improve the capabilities of our integration algorithms. Yeah, so I was asked to talk about the SymPy's assumption system. Apparently this is of interest to Sage, so I'll go into this in a little bit of detail here. So the assumption system, just in general in a symbolic, in a computer algebra system, is what lets the user define restricted domains on variables. So for example, saying that X is a real number. So by default, SymPy will assume that any variable is just a generic complex valued number, and it's not going to perform any sort of simplification or operation on that variable or an expression containing that variable unless it's true for all possible complex values that it could take. So for example, a simplification you might want to make is square root of x squared equals x. This is only true if x is actually a non-negative real number. So if you know that x is in fact a positive real number, you can define this assumption on x and actually allow the simplification to take place. In many cases, closed form solutions to problems will only be possible under restricted assumptions. So it does let things simplify more. It also is basically essential for actually allowing certain things to be computed. SymPy, the assumption system in SymPy is a little bit complicated. It's somewhat of a mess, to be honest, but we have two assumption systems basically, which we sort of colloquially call the old assumption system and the new assumption system, which just a little tip for everybody, never ever call something old and new, because right now the new assumption system was created in 2009. It's no longer a new assumption system. So if you want to name something, name it differently than that. But the old system is something that dates back to the earliest versions of SymPy. So the basic idea of the assumption system is based around a three-value logic system. So everything is either true, false, or a third value, which we use the Python none object for. None means unknown, or it means like it can't calculate it. So the basic rule is that whenever you have an operation with a Boolean operation with none, if the result would be the same thing, if none were replaced with true and with false, then it gives that. Otherwise, it sort of bubbles up and keeps it as none. So for example, here, true, if you do an OR operation with true and none, if you were to replace this none with true, or with false, the result would still be true regardless. So this would give true. On the other hand, true and none, if this none were true, it would be true, but if this none were false, it would be false. So it sort of bubbles up as none. So the way that works is here with the old assumptions system works is that you sort of, whenever you create a symbol, you can define these assumptions on it. So X here is defined to be positive. And then these are queried with this is underscore assumption attribute. So X being defined as positive, it now knows that X plus 1 is also positive. If we had not put this positive thing here, this is positive, X plus 1 is positive would have given none, because it could be true or it could be false. And so the deduction in this old assumption system is done just using a rule-based inference algorithm. There are several sort of basic implications on these assumptions that are defined. So for example, it knows if something is defined, if something is positive, then it also is real. And then there are more complex things are evaluated using methods on the class, on the respective classes. So here the class for power has a method on it that evaluates if a power is even. So for example, here, if the exponent is an integer and it's also a positive integer, and the base of the power is an even number, then it knows that it's true that the power is even. And you can see here, if it doesn't hit this return statement, it'll just return none. So this the benefits of this particular model of our old assumption system is that it's relatively fast and it works for most things. This syntax here, as you can see, it's pretty intuitive. It's pretty simple, easy to type. And this has been the primary assumption system that's been used throughout SymPy for basically ever since it's existed. There are some limitations to this particular model. One limitation is that because the assumptions are defined on symbols, you can't sort of assume things about larger expressions. So it's impossible, for instance, to assume that X plus 1 is greater than 0 here, because there's no sort of is greater than -1 assumption. There's only a positive assumption, and you can only define the assumption on this X variable here. There's also only just a fixed number of predicates, like positive, real, even, and so on. And so it's difficult for users to extend the system with other ones. Handlers like these handlers have to be defined on the classes, which also limits that user extensibility. That it's difficult for a user to sort of extend the logic here to say, maybe tell POW that even is something stronger than this particular logic. And one of the other big limitations is that this 3-valued logic I mentioned with true, false, and none is used here in these handlers. So if you look closely here, you have to sort of be very careful whenever one of these assumptions is used, because none in Python actually is sort of evaluated as a false value. So you have to be careful if you ever have like a not in Python. You have to be careful if the thing that you're doing not with can be none, it might actually be incorrect, because not none in the 3-valued logic should be none, whereas in Python, not none will give true. So you have to be very careful. It's very error prone doing it this way. There's also the new assumptions that I mentioned, which are not that new anymore, but they're still called that. In the new assumptions, the assumptions are separated from the objects themselves. So instead of defining X as being positive, you create a separate object, this queued up positive X, and this represents the predicate of X being positive. One benefit of doing this is that these predicates can now be combined into arbitrary logic expressions just by using the logic module of SymPy. So this vertical bar here means or, and so this expression here means X is positive or X is even. Queries are done with this ask function. So this here ask q dot positive x plus 1, q dot positive x is basically the same thing that I had on the previous slide. It's asking, given that x is positive, is x plus 1 positive? And another difference here is that with the old assumptions, simplification is just done sort of in the simplification algorithms by looking at the assumptions. Whereas in the new assumptions, since they're separate from the objects, there's now a separate function called refine that will take some assumptions on variables or expressions and simplify them. So here we can see sort of we're able to assume that this x plus 1 expression is positive and simplify this. This is something that would be difficult to do with the old assumption system. In the new assumption system, the facts are represented as expressions, logic expressions, using the same logic system that the SymPy has. Here, the fact that being positive implies being real is just represented by this logic expression, and this is just it's the same kind of expression as any other SymPy expression. You can manipulate it in the same way that you would any other SymPy expression. You can look at its .args. You can print it. You can do whatever you want with it. So it's making full use of the expression system. More advanced facts are also stored as expressions. So instead of using Python logic like we were doing in the old assumptions here, we actually have expressions representing facts. So here's some facts that are defined for the power object. So you can see, for example, here it's saying that the base being real and the exponent being even and the exponent being non-negative implies that the entire power is itself non-negative. These this shift operator is overloaded to mean logical implication in SymPy. And so this exact design that I showed here, especially for these handlers, has been evolving, and so we may modify it in the future to be more useful. Presently, all the deduction around these facts is done using a SAT solver. SymPy has a pure Python implementation of a SAT solver, or you can also optionally use a faster C SAT solver. So some of the benefits of this design, like I said, you can create arbitrary logic expressions with these predicates. So here I'm asking, given that x is real and not 0, is x positive or negative? And the result is true. And this is this is something that's impossible with the old assumptions. The old assumptions, you can do this right part. You can say x is real and not 0, but it's impossible to ask if x is positive or negative. You can ask one and it'll tell you none because it doesn't know, and you can ask the other, it'll also give you none. There's no way to ask the combination, which is actually true. It's much easier for users to extend the assumption system with custom assumptions. You can easily define these predicate objects on this Q object here to be whatever sort of predicate you want. You can also easily add custom facts just by including them here. And when you call ask, you can easily sort of tell ask about any sort of fact that you know about these assumptions, and it'll include it when it does the SAT solve. You can assume things on arbitrary expressions, as I've mentioned. Representing these facts as expressions makes them much more readable. Compare, for example, this, which is actually 4 different things to what we had before, which is would be just one of those things in Python. And also being expressions, it gives it opens the possibility for things being much more legible. You can print expressions. You can do interesting things with them. You can do. There's even possibilities of like using the SAT solver to sort of tell you about if your assumptions are inconsistent, maybe try to find a unsatisfiable core and actually give it a useful error message as to why things failed. And another big advantage is that all of this is using just normal predicate, two-valued predicate logic. So here, none of this is using this this three-valued logic that I mentioned. These are just normal logic predicates. So only the very end, when ask returns something, is it going to actually return true, false, or none. And so this removes a lot of the buggy logic that can happen with the three-valued logic. The limitations are, it's a lot harder to get good performance with this. That's one thing that we've been trying to work on, and there's still some work to do. Another limitation is that the assumptions being separate from symbols is a lot more clumsy than attaching to the symbol. It's the actual end user interface of calling ask is for most simple applications a lot more typing and a lot clumsier than just doing sort of .is positive or something like that. And then also a SAT solver is kind of limited in what it can do, and so it might be better to use something like an SMT solver, which I hopefully will learn more about in one of the later talks. The biggest limitation is that very little is actually implemented in this new assumption system. So if you want to play around with it, please do, but don't be surprised if something just doesn't work, because most of the things that are actually implemented are implemented in the old assumption system. So don't be surprised if ask or refine don't actually do anything useful at this point in time. But like I said, for future work, we really need a coherent plan for combining these two systems into just having one assumption system. Initially, the plan was to replace the old one with the new one, but I think it's become clear that that's actually not what we want to do. Like I said, the old API actually has usability advantages, and it's also, frankly, just too entrenched to eliminate it. It's basically used throughout the entire library. We need to improve the performance. We need to come up with some better APIs, and we need to look at using some more advanced solvers so that we can actually take full advantage of the potential of using full expressions. By the way, if anybody is posting stuff in chat, I haven't been following that, so I just noticed that there was something. I guess somebody posted a list of SAGE issues relating to three-valued logic. Presumably, that's to reinforce the point that three-valued logic can be very bug-prone. So now I'd like to talk about some of the current work that's being done in SymPy. The biggest thing that's happening right now is that we have gotten a grant from the Chan Zuckerberg Initiative to pay for 2 core developers and 1 postdoc for 2 years part-time. So this grant is going to focus on documentation, performance, and code generation. So the first part, documentation, is what I have been working on and will be working on. So SymPy has over 1,000 functions and methods, and our API reference documentation is actually fairly decent, but we are pretty lacking in sort of long form tutorial explanation guide documentation that lives separately from the API references. So the focus is going to be primarily on writing new user guides and tutorials. We feel that this documentation is, it ends up being best when it's written by an expert. So that's why I've taken on this work, because I feel that I have expert knowledge of the library. And the focus is going to be on prioritized on the biggest areas of confusion from users via things like the mailing list and Stack Overflows. And actually this last part here is incorrect. That survey was already run. We have a new documentation theme, one of the results of this so far. So I've been working on this grant since September part-time. So here's the old theme that our docs use. You can see that the sidebar here is well, it's kind of hard to read because of the color contrast. You also can't see it in this picture, but it's actually stuck to the top of the page. So if you were to scroll down on this page, you would no longer be able to see the table of contents here. The new theme looks like this. It's a Sphinx theme called Furo. And you can see here on the left, we've got this very nice navigation for the entire documentation. On the right, there's a navigation for the page. Yeah, it supports, it has a bunch of very nice features. It has a dark mode support. It's got this nice navigation. The color contrast is all WCAG AA compliant, and it also has mobile support. In addition, I've written several guides as well and I'm currently working on writing quite a few more. So if you've used SymPy and felt that any areas of the documentation were lacking, or that you wish there were guides for something, please let me know, and I'll make sure to prioritize those over the next couple of years as I work on this grant. For this next part, I think Oscar is going to talk about what he's going to be working on.
Yeah, so when this grant was originally supposed to pay for me to work on performance for 50% of my time this year, well, this academic year just gone, and the next academic year. But I think the grant came in something like August last year. And when I went and spoke to my head of department, they said that it was going to be very difficult to get me out of teaching for the year. So in the end, it's now paying for me to work full time over the next academic year. So I haven't actually started any of this work yet. But the idea is, well, Aaron will be working on documentation, or will be working on performance issues around the SymPy code base. So performance issues are a major issue in symbolic computing in general. So we've heard Fredrik talking earlier about how much work they've done in FLINT and these other libraries to make performant algorithms, but still I think you'll find even when things are in C, they can still get very slow. In the context of SymPy, many parts are just really not very well optimized. So I think it's quite common that features are contributed without really being tested on particularly large problems. And in fact, in many cases, fairly basic things could make it a lot faster. In some cases, the slowness of things, it can make SymPy unusable for various problems. So if you wanted, so Aaron mentioned a lot earlier the idea that SymPy is used as a library. So if you wanted to use SymPy as a library as part of some sort of end user application that solves some particular problem, you don't want to have something like a solve function that could potentially take years to return a value. So you need something that can give you a reasonable result most of the time in a reasonable time. So the goals of this project, generally speaking, is to make SymPy faster. And the first step in that is to generate some meaningful benchmarks. So at the moment, SymPy has a benchmark suite which tests the speed and which is supposed to discover when something has slowed down as a result of some sort of change. But there are some significant problems with that benchmark suite. So one problem is it doesn't really take into account caching. So it actually, the times that it reports are actually, so SymPy compensates for poor kind of algorithmic performance in some areas by making use of a cache that caches previously calculated results. But that cache, because it's running during the benchmarks, it means that the results from the benchmarks are completely meaningless a lot of the time. So I want to get those meaningful benchmarks in because that's how we lock in the performance benefits. So if we do make things faster, we want them to stay fast in future. So we need to be able to measure that speed. So we want to use better algorithms in a lot of places. So one of the big areas where SymPy's algorithms are quite weak is in polynomial GCD, so greatest common divisor. So part of that part of that means kind of fixing the code in SymPy so that it works better as a standalone pure Python library. But also, what we really want to do is make it possible to use FLINT and or potentially other libraries like that. But FLINT in particular is the target at the moment. So I want to. Fredrik was talking a moment ago about the Python FLINT module. So I've done a small amount of work so far on trying to make that more easily installable, so you can just easily pip install the library. But it would be a much larger amount of work to actually be able to make use of that within SymPy. Okay, so it provides all the things that we clearly need, that we clearly want. So fast polynomials is the big one. There's also all the matrices of integers and rational numbers and so on. So there's already something sort of like that within SymPy. And that already can make SymPy a lot faster, although it's not used yet. But if we can also delegate some of that work down to FLINT itself, then there's a potential for some problems to get much, much, much faster in SymPy. So we also need to do a lot of micro optimization. There are many places in SymPy where it's just a very small kind of poor decision in the code results in things slowing down quite a lot, and it just takes a bit of analysis on important use cases to identify those. And so the goals, we are talking about things like factorizing polynomials and so on using FLINT. Our real goal is here to focus on where people are actually using SymPy in scientific applications. So under the hood, that might involve factoring polynomial. And so we want to make that faster, but that our key focus is on those sorts of areas, which is mainly around things like solving equations and occasionally around things like calculating integrals. So Aaron, can you pop over to the next slide? So I want to mention this here since we're talking with people from Sage. So I'm interested in the potential for collaboration. So one possibility here is I want to make a good benchmark suite, but I see and a good test suite for different algorithms and things. But I would really like these sort of benchmarks to be something that can be shared across multiple projects. So not just for use by SymPy, but also for use by SymEngine or perhaps Sage, or perhaps various Julia libraries and other things. So it's a lot of work creating these benchmarks. It should be something that we can share across projects rather than just being specifically part of SymPy. So many different projects currently duplicate this sort of work. And even though there are things like, so for example, in the context of solving differential equations, you have what's often referred to in academic papers as the Kanker test suite, which is just a large set of differential equations that were symbolically solved in an old textbook. So things like that, it should be easy to access those and share them across projects so that you can quickly test your integration algorithms or your differentiation algorithms or whatever else it is, both in terms of test suites and also in terms of benchmarks. So that's one area where I'm interested in collaborating with other projects. And lastly, they're improving the FLINT wrapper. There is the possibility that SymPy and Sage could share a single wrapper for FLINT. And again, this is something that Fredrik mentioned earlier. So neither of the existing wrappers exposes the newer FLINT features. And so there's a bunch of work that should be done to do that. But that work would obviously be duplicated if there are multiple wrappers. Okay, so that's what I was going to say for there. Aaron?
Okay.
Yeah.
Yeah, and so the final part of the CZI grant is going to be focusing on code generation. So we are, Jason Moore at TU Delft is hiring a postdoc who will be working for 1 year, focusing on improving the usability and performance of code generation and developing a benchmark use case for an advanced biomechanics benchmark use case. So we'll be announcing this postdoc hiring very soon. If you watch the SymPy mailing list. So the goals here are, like I said, it's going to be focusing on building a biomechanical model to benchmark the code generation. And the goals here are to sort of integrate this code gen package into high-level functions and classes. So we have a submodule in SymPy that allows representing sort of high-level constructs for code generation. Things like you can represent things like for loops or function definitions as expressions. But right now, this is not fully integrated into the actual parts of code generation that actually generate the code. So doing this will allow generating much more sophisticated code. For example, there are certain sorts of functions that if you want to generate code for a language like C, it would require actually writing a loop in C. And so right now that's not possible because, or it's not very easy to do because it's difficult to represent that without actually being able to have a high level representation of things like loops. We're gonna, another focus will be on numerical accuracy. So trying to rewrite expressions in ways that will avoid floating point errors, improving the general speed of code generation, developing optimizations that can be done symbolically, and yeah, just general support for different things that come up in code generation. So another thing that's currently happening in SymPy is we have some Google Summer of Code contributors who are going to be working with us this summer. So we have 3 people. Timo Stinestra is going to be working on the mechanics module. Advait Pote is going to be extending the continuum mechanics module and the physics submodule. And Anutosh Bhatt is going to be improving the series expansion and limit computations. And I apologize if I've mispronounced any of those names. And then finally, we are also participating in Google's Season of Docs program. So Jeremy Manat is working with us to write some guides and improve our user guides specifically for the solvers submodule. So future work, as we talked about, we're always wanting to improve the performance. Hopefully we can make some pretty big strides in that with Oscar's work. We always want to implement better algorithms so that we can actually compute more things. The assumption system, as I mentioned earlier, it could use some cleaning up, and that also actually kind of ties into these previous 2 points as well. Some of them are sort of blocked on having better assumptions. There's also the solvers module also can use some cleaning up. We're hoping to apply for more grant funding similar to the CZI grant so that we can actually pay core developers to work on some of these things. finally, we have a roadmap that sort of outlines some of the other things that we would like to work on. So I think we've got a few minutes for questions. I don't know if anything else was posted in this chat.
First of all, thanks a lot. And we do have time for questions.
Can you say anything about this awesome support of SymPy by the Chan Zuckerberg initiative? That's really cool that they're supporting math software, and I'm really happy to hear about that.
Yeah, so actually this round, this EOSS4 round here, cycle 4, and actually some of the previous rounds as well are supporting quite a few sort of core libraries. So CZI, the sort of broad goal of CZI is sort of to support biology and biomedicine. I think their overarching goal is to cure all human diseases by the end of the century, but they're very supportive of infrastructural projects. So some of the other projects that are being supported include Jupyter, scikit-learn, and NumPy. So they're very they understand that these some of these libraries are very core to the science that they want to support, and so and they're also very very sort of open to sort of supporting maintenance work on these libraries. So you can see that the work we're doing here, other than the code generation, which sort of is going to have a biomechanical model that guides it, it's sort of very general maintenance work that is happening. It's maybe not directly obvious how this impacts biomedicine, but there is a direct impact, because improving the performance of SymPy, for example, will make it much more usable for scientists who are trying to use SymPy, and the same thing, of course, with documentation. So yeah, the Chan Zuckerberg initiative has really been great for supporting this sort of infrastructural sort of work in open source, the scientific open source ecosystem. And yeah, I agree with what was put in chat, that Fredrik should look into it. I think the most recent round, I believe, is closed now, the call for cycle 5, but I think they typically have yearly calls for this particular grant, this EOSS.
I mean, potentially there could be the possibility of, because we will be looking at applying again at some point in future. So there's some potentially we could talk about collaborations for then. So it's important to understand that from their perspective, it's about science rather than maths. And so SymPy, we were able to make the case that we were being used as part of a scientific ecosystem, whereas had we looked more like something that's just for pure maths, then I think I'm not sure that the people reviewing our bid would have felt the same way.
Yeah, definitely. So yeah, they do need to be able to see sort of the path to biomedicine, which is their sort of stated goal. But they are definitely have sort of been willing to fund things that have sort of a longer path than many traditional funders have in the past. Whereas this grant itself isn't directly working on the science, but it's working on the infrastructure that supports that. Someone posted in the chat, one of the ways that SymPy is used in Sage is in the manifolds module.
Yes, if I can comment on this, or
yeah, sure.
I have a question regarding this. Yes, you were asking of an example of use of SymPy in Sage. So we're using it as a symbolic backend for computation on manifolds in a given chart. I mean, symbolic computation involving the coordinates in a given chart. So there are two possibilities, either to use the default, which is Sage default Pinac, or to use SymPy. But I have so it works, it is implemented, but there is a severe limitation at the moment, is that Sage assumptions are not passed to SymPy on a given chart. For instance, you can have a given chart when one of the coordinate is negative, for instance, or as a certain constraint. So it's useful to make simplification, of course, to know these assumptions. So my question is, we plan to do this, I mean, to translate Sage assumptions to SymPy's one. So my question is, should we use the new or the old assumption system in SymPy to do this? What would be your advice?
I would recommend using the old assumptions at this time. Like I said, that there's the new assumptions have a better design, but not as much is actually implemented on them. So if you try using them, you're going to find that quite a lot's just not going to work. If all your assumptions are things like positive or negative, then they should be perfectly expressible.
That we have x plus 1 be positive or something more complicated than simply being positive. You see, we have typically on a subchart, we define sometimes subcharts on the manifolds with some constraints. And so it could be something like, yes, sign of x is negative or something.
Right,
like that.
right. I mean, so I don't know, it might be better to write to the mailing list about this actually, or open an issue on the SymPy issue tracker, because things get more complicated in that case. But so is there a point, does the actual SymPy Sage interface just need improvement there to pass assumptions around? Because I know there has been some work on that recently, but if that's not passing assumptions around, we should improve that so that it does that.
So I think we need to move on to the next talk, but if Europeans can still wait until after this talk, there will be time for this more general discussion. And yeah, I had hoped, in part motivated by the needs of the Sage manifolds and yeah, regarding assumptions, in particular local assumptions that are only hold within the scope, that we can tap into, the knowledge of the SymPy people who have maybe new, maybe old, but definitely cleaner than what we have on the Sage side. And so I think there's plenty of possibility for cooperation there. Okay, but now it's time for our next speaker. So thanks again for Aaron and Oscar for presenting. And we'll now have Gereon Kremer speaking about satisfiability modulo theories for arithmetic problems.
Hello, can you hear me well?
Yeah.
Okay, great. Yeah, thanks for the invitation. I'm currently working on SMP solving for arithmetic at Stanford University on CVC5. And I was asked to give a bit of an insight on what SMP solvers do on, in particular, nonlinear arithmetic, and maybe how this may be of use to Sage and related projects. Of course, I'll happy to be to answer any questions about using SMP solvers in general, if they come up. So yeah, I'll give you a rough overview over what people are doing in SMP solvers. Not all of that is implemented in CVC5 in particular, but all of this is implemented in some SMP solver. And of course, this is not my work. So part of that is my work, and there will be a certain focus on that, but most of it is other people's work. So not claiming anything here. And please just ask whenever you have any questions. I'm not sure I see the chat though. Let me see. Yeah, I can see the chat. Great. So I don't expect everyone is perfectly familiar with satisfiability modulo series, so I give a quick introduction into that. So the basic question we are trying to answer is the following. Given a logical formula phi, is there an assignment to the variables in phi, whatever they may be, such that the formula evaluates to true? And in this, we assume phi is a first order formula, and we'll see in a second what that means. And so we first concentrate on this purely existential case. And when we say first order, it means we have a formula with a Boolean structure, and instead of just Boolean variables, we can have constraints from what we call a theory, and the theories can be all kind of stuff. A lot of that is more directed to people talking about computer programs, for example. So you would have bit vectors and floating points, which roughly correspond to your native C, C++ types. But we also have stuff like arithmetic. And when we say arithmetic, we mean either integers or reals, and that would be arbitrary sized integers. And reals would either be rationals or, yeah, whatever you can express in your theory. In nonlinear arithmetic, that would be algebraic numbers. What may be suspiciously absent from this list are complex numbers. And to the best of my knowledge, no one is doing complex numbers in the SMT community. There are also a few other things, strings, arrays. Yeah, if you're interested in that, I'll be happy to chat about these. And of course, on the other side, the base question is fairly restricted. But there is a bunch of extensions. So for example, if we say the formula is satisfiable, then of course we may want to know what is a satisfying assignment, and we call that a model. If we say it has no solutions, you may want to know why that is, and then we can generate unsat cores. You may be a bit more flexible with quantifiers, so you may want to do explicit quantification. You may not want to have any solution, but maybe the best solution, whatever that means to you. There are things like interpolants. You may not trust our code base, and I could very well understand this sentiment. And thus, for CVC5, we have done a big push to generate formal proofs that you can then feed in for example, Isabelle or Lean theorem prover, and in this sense, increase your trust that when we say it's not satisfiable, this actually is the case. Okay, so how does SMT solving roughly work? We usually split the work between a SAT solver, which is what in the previous talk was already mentioned, which deals with just the Boolean structure, so a propositional formula, and a series solver, which then deals with a set of theory constraints. And what the SAT solver does is it takes a formula, and we assume for now the formula is in conjunctive normal form. So you have a disjunction and then a conjunction. You have a conjunction of disjunctions of theory constraints. And the SAT solver tries to satisfy the Boolean structure, but does not really look inside the theory constraints. And it does that incrementally. So it guesses a bit and then asks the theory solver, hey, is this set of constraints consistent? So is there a solution for this set of constraints? And the SAT solver, the theory solver will then do something which is very specific to the theory and will somehow come up with a solution to this question, either by saying, yeah, it's satisfiable, and by the way, here's a model, or it will say, oh no, that's not satisfiable, and here's a subset of constraints that is already conflicting. And the SAT solver, when it's satisfiable, it will just continue from there and extend its model. And in the case of answered, it will try to learn from that and be clever, exploit this knowledge, and then continue. And the result is either the subsolver gets a full assignment, so that at the end it can say, yeah, the overall formula is satisfiable, and by the way, here's a satisfying model. Or the other way would be that it cannot find a solution for the Boolean structure, which the series solver says, yeah, that's fine. And then it's unsatisfiable. Yeah. So for the sake of completeness, in this talk, I'll focus on the series solver part, and in particular, what kind of series solving techniques we have in our community for nonlinear real arithmetic. But as I said, I'm happy to answer any question about other parts of the solver or other theories. There are other frameworks or solving paradigms, so other ways to approach this. One notable in particular for nonlinear real arithmetic is called an LSAT or MCSAT, where you don't have the strict distinction between the subsolver and the series solver. Yeah, but I just want to mention it. It's not the only way, but it's, yeah, pretty much every SMT solver mainly uses the approach I've sketched here. It's called CDCLT because, yeah, that's what we usually use it for. So when we say nonlinear real arithmetic, what we mean is what mathematicians call the theory of the reals. So, and that is, we have real variables, we have constants. The constants are rational or integer, doesn't really matter. We can add and multiply, and then we have the usual arithmetic relations. And the intuition is we have polynomials over real variables compared to 0. And this framework includes relations over two polynomials. You can have rational constants, you can have divisions, but it does not cover stuff like transcendental constants. So you cannot express pi with that. You cannot have a sine function or a cosine. You cannot have an exponential function, this stuff. And the reason for that is that the theory of the reals is a very nice mathematical framework. This does not necessarily mean it's easy to solve, but at least it is very well defined, and there are solutions how to deal with that. As soon as you add like a sine function, it becomes undecidable, and all that you can do is incomplete, and it kind of changes the whole approach. So for the purpose of this talk, and I'm well aware the statement is not true as it stands there, and there are people that may strongly disagree, but for the purpose of this talk, I'll say that linear arithmetic is a solved problem. So use simplex, and for some specific questions, you may use the Fermat-Skin variable elimination. But yeah, I consider it solved for this talk. And the reason is that if you have a nonlinear problem and you assume you linearize it and use simplex, and if this becomes a problem performance-wise, then most of the time don't even consider using a real nonlinear solving technique, because at least in all the problems we usually face, solving the nonlinear part is so much more difficult than the linear part that, yeah, if simplex starts getting slow, there's no point in looking at the nonlinear part. So linear arithmetic is a solved problem for this talk, and so is the Boolean satisfiability problem. So if your SAT solver starts getting slow, forget about nonlinear arithmetic. So in a nutshell, and I expect, so people here in this audience that know about nonlinear arithmetic have a good chance at knowing more about the mathematical background than I do. But still, as a quick recap, it's complete. So there's a decision procedure, which means there's an algorithm that always gives you the correct result and always terminates. And it admits for quantifier elimination, which is a very nice feature because it immediately gives you all kinds of procedures you can do in the theory, which is not to say that it's easy to do in practice and efficient to do. It just means that a lot of things are conceptually easy once you have this decision procedure or quantifier elimination procedure. There's a bunch of methods. So in the 50s, there was the first complete method by Tarski. Unfortunately, it has a non-elementary complexity, which means its worst case runtime is bounded by a tower of exponents that is not constant size, but it depends on the number of variables. So it's horrific. Then, of course, there are Gribner bases. They are great for what they can do, but they have a limited applicability because they essentially only deal with equalities, or implicitly with equalities, because they only look at the polynomials. And there are techniques in applying them or re-encoding inequalities. But yeah, it's sometimes works. More often than not, it does not work very well. And even if Gribner bases, you can use them, they still usually only give you an answer on complex models. But we are usually interested in real models, so there's this gap. And also the question is, even if Gribner bases tell you there's a model, it's not clear how to get to it. So, and when I say it's not clear, it's at least it's not easy to do. And it's a whole different problem in how to do that. So then there is cylindrical algebraic decomposition, or CAD. And this is the de facto standard quantifier elimination procedure we have to this day. It's a complete thing. It's great. It has doubly exponential complexity in the number of variables, or to be more precise, in the number of quantifier alternations, which is bad, but the best we have. Then there are a few incomplete methods: virtual term substitution, interval constraint propagation, subtropical satisfiability, linearization. I'll tell you later a bit how they work and how they're incomplete. And finally, there is a new variant of CAD that we have worked on, which borrows all the theory from CAD, but seems to work way better in practice. So much of this is of what I'll tell you has been done in the context of the SC² workshop project, which is like a collaboration of SMT people and computer algebra people to join strengths and bridge these two communities to solve exactly this kind of problem. And if you actually want to go into depth for a lot of these issues, you should actually talk to someone on this list. And I shall be happy to tell you which exactly that would be. Okay, so what I'll do in the rest of the talk is essentially a quick run through all of these methods. And I will not attempt to give you an in-detail explanation for any of these, but rather a rough intuition of what the method does and what you can expect if you use it. So incremental linearization is exactly what the name tells you. It will attempt to linearize your problem and do it in an incremental fashion such that you don't overwhelm the solver immediately with everything you know. And what you start with is whenever you have a multiplication, you implicitly abstract it by a new real real variable. So for example, if you have these three constraints, x greater 0, y greater -1, and x times y smaller than 2, then this x times y will be considered a fresh variable you don't know anything about. And you just give that to a linear solver, let it solve it, and then you look at the model and try to figure out, okay, why is this model bad? So if it works for the nonlinear part, everything is fine, you got lucky, but most likely it will not satisfy any of the axioms for your multiplication. And what you then try is you look at the axioms for multiplication and instantiate them in a clever way. So for example, here you would say, okay, if y is 0, x times y cannot be assigned to something else than 0. And you could generate a lemma exactly like that and hand that over to the linear solver and have the linear solver continue. It gets a bit ugly. So for example, in this case, if you have 3 and 1 and the multiplication is not 3, then you might be tempted to just add a lemma that says, well, x is 3 and y is 1, then the multiplication must be 3. The problem that you then run into is that what if y is 1.1? And what is if 1.2? And what is if 1.3? And then you just end up generating a whole bunch of lemmas, and it will not terminate most of the time. So what we do instead is we look at the tangent plane of the multiplication and the tangent plane at x equals 3 and y equals 1. So in the first Taylor approximation at this point. And based on this tangent plane, you can generate a nice lemma that is linear and gives you a lot of information. And this is essentially the whole idea. And you do that in a loop. Sometimes this is surprisingly strong in finding unsatisfiability. Sometimes you get lucky and find satisfiability, and sometimes you get unlucky and run into non-termination. So this is just an overview over the kind of lemmas. The details don't really matter. The main point here is that most of the lemmas are really easy. So if you happen to have a linear solver and want to add some support for nonlinear arithmetic, this is pretty easy to do, and it's surprisingly effective. So the problem is identifying models, because sometimes the model is just not rational, and then the model construction part is in simplex, and simplex will only generate rational models. The great thing here is that it can easily be extended to transcendental functions and other operators. So maybe one question we as a community have to your community in the broadest sense is whether there are clever new linearization lemmas we can use. But maybe not a discussion for this talk. Okay, there's another thing we call interval constraint propagation. And the core idea here is that you have some constraints and you always maintain the current search space. And for example, initially you start with -infinity to infinity, but maybe from the constraint y greater than x squared, you can immediately derive that y must be positive. And then you shrink your search space. So you always have a box in the search space. And you always make your box smaller. So for example, now you take this constraint, you plug in your current intervals for x and y, and then you do regular interval arithmetic and get a smaller interval for x. And you continue doing that. And for example, for this example, you would end up with the box from 0 to 1, which is not a solution yet, but it makes you have reduced your search space significantly. And sometimes you can also just guess a midpoint, for example, and get lucky and see a solution. So the implementation is a bit tricky because you need a library that does all this interval arithmetic stuff well. And most likely you are doing that on double intervals, and you get into this whole business of rounding mode so that you are guaranteed to over approximate. But there are intervals like boost interval, and there are a couple of others that already implement that. And if you use one of these libraries, it's fairly straightforward to implement. It's more a matter of parameter tuning to get all that right. And then you get a fairly effective method that is, in particular, it's great in combination with other methods because it just shrinks your search space very efficiently. And there are a couple of solvers that are solely based on that premise. Problem is you need some sensible initial bounds for a lot of problems. And this may actually relate to what the previous talk was about. So probably you can use some of the assumptions as initial bounds that are already strong enough to do something here. Then there's an interesting approach called subtropical satisfiability. And like the the explanation in one sentence is you reduce the problem polynomial is equal to 0 to a linear problem in the exponents of p. And what this linear problem is essentially saying is, has a polynomial a form such that if we let the variables grow in a certain direction, that one monomial in your polynomial will eventually dominate all the other monomials. And the direction in which you grow is essentially the exponent vector of this polynomial, of this monomial. And if you then grow into this direction, then well, it will eventually dominate that, and that means if you go far enough in that direction, the sign of this monomial will be the sign of your polynomial. And then there's a bit of technicalities around that, but this is, in the end, you get an incomplete procedure that uses linear constraint solving to certify that your nonlinear problem has a solution. And the really great thing is that it does not grow, or the difficulty of your problem does not grow with the number of variables. Sorry, with the number of, yeah. So it has very nice scalability characteristics, and there are certain patterns where it works extremely well, so certain problem structures. And yeah, if you know that your input has a certain structure, it's definitely worth trying that out. If it works, it's super awesome. If it doesn't work, okay, then yeah, that's sad, but also you don't lose a lot, because if it doesn't work, it will know so very quickly and you have lost a lot of time. Okay, yeah, there's a bit of technical explanations there. Yeah, then there are Grübner bases. I already mentioned them. I expect that most people here probably know more about Grübner bases than I do. So you generate canonical generators for polynomial idea, and from my point of view, it's just a normal form for a set of polynomials, which maintains a set of common roots. And it underlies a whole bunch of computer algebra problems. There are extremely major implementations in every computer algebra system out there. It's in worst case also doubly exponential, but in practice it's usually much, much faster. The relevant property for us SMT guys is, yeah, this. So it's the SMT problem, but over the complex numbers. And the problems we try to deal with is, so when we try to use them, what about inequalities and how do we go from the complex numbers to the real numbers? There's been some work there. And yeah, there's no real good solution, unfortunately. And there's still open question in how do we construct models and how do we obtain infeasible subsets. So assume the Grübner basis is 1, so the reduced Grübner basis only has a constant in the end. Then can you give me the set of polynomials that was sufficient to make the Grübner basis become 1? And from all the implementations I've seen out there, this information is lost because, well, usually people that use Grübner basis don't care about that. Yeah, but it would help us a lot. There is virtual substitution. The core idea is that you eliminate variables using the solution formula for polynomial equations. And with solution formula, I mean what you know from high school. How do you solve a quadratic equation? And use that to solve a polynomial. And then you substitute the values into the remaining equations. And there are some clever tricks how to deal with inequalities. So that's why it's called virtual substitution. You get virtual values which are -infinity or some value plus epsilon. And then you have special substitution rules that deal with that. They look somewhat like that. So they're not that difficult. It's just a bunch of them and you have to implement them. The problem is they're not always applicable. So to do that, you need these solution formulas, and they only exist up to degree 4. And so that means if your problem has higher degree polynomials, you can't use virtual substitution. And also when applying a rule, you may exhibit a degree growth. So even if your original problem formulation is just quadratic, you may, while doing virtual substitution, hit polynomials that have higher degrees. If it works, it's super nice. It's comparably efficient. It's singly exponential, which is, yeah, it's bad, but not that bad. Pretty good compared to the alternatives. There are extensions to allow for arbitrary degrees, but essentially the intuition here is that you have a database of pre-computed parametric quantifier elimination rules. So it's like, yeah, a bit difficult to say whether you honestly think this is a good solving technique. It depends on your application, I would say. Okay, now for what I've mostly done. So this would be the part where I can also answer much deeper questions, I guess. Cylindrical algebraic decomposition. The goal is to be able to deal with any polynomial systems. And the core idea is that you look at sign invariance. And that means, so the main observation is, if you have a formula that only deals with polynomials compared to 0, then if you have 2 points, and for these points, all polynomial have the same sign, then the formula evaluates to the same truth value. Because you only compare to 0, which means if the signs are the same, the constraints evaluate to the same value, and then the formula evaluates to the same value. And this means that if you have 2 points where all the polynomials have the same sign, these are for this purpose, these points are equivalent. And what CID tries to do or what it does is it constructs a decomposition of your multidimensional space into what we call cells that are sign invariant. And when they are sign invariant, that means within one cell, the formula for every 2 points within a cell, the formula evaluates to the same value. And that in turn means you only need to consider one of these points, because you know if one of these points satisfies the formula, all of them do. And this gives us a nice abstraction from our uncountably infinitely large search space R to the n to a finite number of cells, given that we have a finite decomposition. But CID will give us that. And yeah, looking at the picture, it is rather intuitive. So assume you are in 2-dimensional space, and the 2 lines, so the 2 polynomials, are the roots of the functions you're actually looking at. And the solution space is the intersection of these 2. So a constraint is satisfied in the shaded areas. Then we can say these are the sign invariant regions. And in addition, to these open regions, we also have the root surfaces themselves, of course. And then instead of looking at at the whole geometric object of a cell, we can instead just look at a single point. So for example, the black dots here. And in practice, of course, it's a bit more ugly. You will you will have to consider much more points, and for the reasons of how you construct them, they will be arranged in what we call cylinders. But at the end, you get a finite number of points, and you can just go over them and check whether they work. And the rough idea is you project dimension-wise, and you look for critical points, which are points where the arrangement of cells changes. So if you imagine we ignore the y dimension for a moment and only look on the x dimension, so on the axis below the coordinate system, then the question is to get to the critical points. When we move over the x-axis, where do cells start or end. And these, when the constraints intersect, so when we come from the left, then at the left point, suddenly the cell in the middle appears. It comes to be at this point, and at the right point, it stops. And what CAD does is it identifies these points, and if you do that properly, then you get these points just on the x-axis, so the second and the fourth point that are pointed to by the vertical arrows. And the interesting thing here now is that all the points in between these are equivalent, in the sense that over all points in between them, the arrangement of cells over them, so in the second dimension, is identical. And then you can lift them and get all these points. And the implementation goes kind of the other way around. You first compute a bunch of polynomials and then lift from there. And this gives you a nice, it's not exactly recursive, but a dimension-wise procedure on how to do that. And you get two main components. So one is projection, where you compute a bunch of polynomials. It is mostly based on multivariate resultant computations, in case anyone cares. And you compute resultants, discriminants, and take coefficients. And essentially, what these components just like check all the boxes of cases that may make these cells appear or disappear, in the sense when you go over the lower dimension and look up what happens over these points. And lifting is then you take a partial sample point, and the sample point may now be an algebraic number, real algebraic number, and a polynomial. You then substitute this partial sample point, you get a univariate problem, and you then do real root isolation on this univariate polynomial. So this is a rough idea. A few final notes. The asymptotic complexity is, I would argue, as bad as it gets for algorithms that are actually used in practice. So it's doubly exponential in the number of variables. If you look very closely, you can do it in doubly exponential in the number of quantifier alternations, but you need quite some insight into your problem structure to do that. Oftentimes it's way faster. So if you have a problem in practice, you have a good chance it works better than that. But this doubly exponential behavior, it's not a purely pathological issue like some argue it is for Gribner bases. This happens on real problems, and you need to be aware of that. And if you use it, you will eventually see problems where it behaves very badly. But it's a best method we know that is known and implemented. There's a lot of active research on that, but it needs a lot of basic algorithms to be implemented. And when I say basic, basic involves stuff like multivariate factorization, multivariate GCD, all this real algebraic number stuff. And yeah, it's hard to find good implementations that you can use as a library, unfortunately. And then the new thing that we have worked on is conflict-driven cylindrical algebraic coverings, which is essentially you take all these CAD techniques, but use them in a conflict-driven way. And by conflict-driven, what I mean, you start with generating these partial sample points, and then see what they do, essentially. And if they don't work, only then you use these CAD machinery to learn why they don't work and which part of the search space you can exclude. And so the intuition is, we just guess a value, and then we plug in this value into now univariate constraints and see for the next variables which intervals now in this next dimension are excluded. And when we have a covering, which means if we have excluded the whole real line, then we look at this covering. Maybe we don't need all the intervals we have generated, And this covering now corresponds to a subset of the constraints. And now we check, okay, which part around our current sample point, so in this case, around x equal to 0, can be excluded for the same reason. And here, this covering can be generalized as long as these dashed lines still overlap. And in this geometric, so if we look at this 2D problem based in the constraint, it means the covering stays intact as long as the two constraints still overlap. And then you are exactly in the CAD scenario where you look for the places where they no longer overlap. And this is exactly the boundaries of the cells we were looking in the CAD case. And we use just a standard CAD machinery and construct and learn that x cannot be within -2 and 3. So it's in this sense very easy, because if you have if you know how CAD works and if you have an implementation of CAD, then you have everything you need for this algorithm. And yeah, so just the ingredients here, you have this real root isolation. Yes, sampling is just, you have a bunch of intervals, find a value that is not in these intervals. You have a recursive call. This is the CAD machinery. And yeah, this is again real root isolation. So there's really no magic here, which is also one of the main selling points of this algorithm in my mind. Because yeah, you also inherit all the nice things from CAD. But it's not just a reformulation. So there's also a nice trick that reduces the overhead in CAD. So in CAD, you compute pairwise resultants of all your polynomials. So that means if you have n polynomials in some level, in some dimension, then you need to compute n squared resultants. And in this method, you only need to compute resultants between neighboring intervals, which in practice makes a big difference. It doesn't save you from the worst case, unfortunately, but yeah, it's one of the reasons it performs pretty nice in practice. And I'll show you some experimental results in a minute. So there are other techniques, of course, and these other techniques are not used in any SMT solver, as far as I'm aware. And I'll give you a quick reason why I think that is. So of course, there's this whole field of numerical mathematics, and I've also tried to work a bit with that in my master's thesis. And they usually focus on a good approximation. And if you just want a solution that is pretty close to your completely correct algebraic solution, that's good, use them, fine. The problem is that it's very hard to get formal guarantees from these algorithms, in the sense that even the guarantee that the solution they give you is 100% sure that it 100% satisfies the constraints, it's very hard to get, because, well, they are subject to rounding errors. And if you can just check, of course, you can take the double results they give you and you can evaluate them on your constraints in an exact manner. And if they don't work, well, you're screwed. So you don't really know what to do then. And we've tried a bit and playing around with that, and it's very hard to do. And yeah, that's why in our community, no one really uses them. Yeah, there's Tarski's method, as I said, complexity is horrific. Yeah, there are two methods that have singly exponential complexity, but they are impractical because it's an awesome achievement from the theory side to have these algorithms, but in some sense these guys have cheated complexity theory and moved all the difficulty from the big O notation kind of into the constants. And you can show that as long as you stay within the size of the universe, they will never be faster than CAD. So Nobody has ever implemented them. Then there is a rather new technique called reliable sign conditions, which is somewhat similar to CAD. It has never been implemented. I'm not exactly sure why. It seems to be because it's pretty complex in the details and you have to consider a lot of corner cases, and yeah, maybe this is a possibility for the future. I'm not sure. And there are some other CAD-based methods that are just, I think, too new to be adopted in our case. Regular change seems to be more focused on the complex case. And NewCut, yeah, is just, yeah, in some sense still work in progress. So maybe we'll come around adopting them at some point. And yeah, if you're interested in using SMT solvers, there are some things we can do beyond QFNRA, so which is our code name for quantifier-free nonlinear real arithmetic. We can you can deal with quantifiers. So though I think none of the major SMT solvers implement that for nonlinear arithmetic, so you can eliminate quantifiers. What most of the SMT solvers can do is they can combine this, so you can use multiple series at once in one formula, and so you can use nonlinear arithmetic in combination with arrays, bit vectors, floating point strings, or what I said before. You can also combine in the sense with transcendental functions. It's then a bit tricky to also use this algebraic routines like CAD, but it works, and it works pretty nicely in many cases. Some SMT solvers can also solve optimization queries. Though when I say here CAD can be used for that, this means I've written down how it should work in my thesis, in my PhD thesis, but this has not been implemented. So if you want to optimize for nonlinear problems with SMT solvers, you will get a fairly generic binary search style optimization procedure. And we can also use all that for integer solving. Yeah, of course, there are also other approaches that go beyond our CDCL style SMT solving. So there is this other approach called MCSAT. So if you just use SMT solvers as a black box, you wouldn't really care, I guess. But if you want more about CAD can also be used in a standalone tool. And they are like the regular computer algebra system, and like QAPCAT is a more specialized CAD targeted tool. Yeah, then I promised some experiments. So there are a couple of SMT solvers around for this. So Z3 used to be the big SMT solver, leading SMT solver. It's from Microsoft. Yikes is from SRI. CVC5 is what I've been working on the last 2 years. Yeah, SMT Red, Verity, Marsat are other solvers. Right now, I'm very proud to say that CVC5 with this incremental linearization and the covariance approach is the best solver out there right now. But if you have specific problem structures, it's definitely worth looking at the other solvers as well. Like Marsat, for example, it really doesn't look that good in this table. But for certain problem structures, Marsat is really good, and you should have a look at that. Okay, thank you very much for your attention, and I'll be happy to answer any questions about this talk, about SMT solving in general. Yeah.
Okay, thanks very much. And we have an unbounded, positive, real amount of time for questions.
I have a question. So if going back to one of your first slides where you talk about how SMT solvers work.
Yeah.
So that I forgot what the acronym was for it, but yeah, the CDCLT. So if you have a pre-existing SAT solver, does this mean that you can sort of take a theory solver and turn that into an SMT solver, or does it need to be more tightly integrated into the SAT solver?
So the selling point is that the answer is yes. So CDCL is what your SAT solver does. So if you integrate picosat or minisat, this is a CDCL solver. And the theory is that instead of so the theory is that after a Boolean propagation, you just hand over your current Boolean assignment to the theory solver. It gives you the answer, and that's it. In reality, if you want to have decent performance, there's a lot of stuff I mean, it's not difficult, but there's a lot of engineering going on. So because this mapping from Boolean variables to theory variables to theory constraints is a bit tricky, and then it's a question. You don't need to consider all the theory constraints, but you can like try to figure out that some of the Boolean variables didn't actually matter for your assignment. Even if you would have decided the other way around, it would have also worked. And if you do that, you make the life of the theory solver much, much easier. So it's a bit both ways. Conceptually, yeah, it's that easy. And all of the SMT solvers use, like CVC5, SMT-Red, and Yikes, they all use a more or less patched version of Minisat internally. But for decent performance, unfortunately, there's more to it that, yeah. But the other way around, unless you give it really difficult problems, any of the SMT solvers will do reasonably well on pure SAT problems. Of course, if you feed it a SAT problem where like a dedicated SAT solver like Cadical or so already has a hard time, then the SMT solvers will not get any better, and they pay a certain price for all this machinery around it. But like if you just have reasonably easy SAT problems, then all the SMT solvers will solve them just fine.
More questions?
What are the reasonably easy instance size?
For CAD or?
In general, yeah, CAD.
Yeah, so it depends really heavily on the problem structure. So if we, in my experience, if we consider problems that come from like computer algebra people, and people have already spent some time of stripping away all the easy scaffolding stuff in a sense, then you can break it with 3 or 4 variables. Usually it scales reasonably well up to like 10. But then the blow up in the number of polynomials really start hurting you. But if a lot of your problem is actually linear, then at least my experience in CVC5 now is that the SMT solver is really good at keeping these away from the nonlinear solver. So for example, if you have linear equalities, it will just eliminate variables using this equality. And yeah, the nonlinear solver will just not see it. And also if in CAD, if in a certain dimension, everything is linear essentially, then also you won't have a blow up there, because all these resultant computations, if you compute the resultant with a linear constraints, the size won't blow up. So yeah, it's a bit difficult to say, but if your real algebraic core of the problem, in a sense, it really gets difficult after 10, I'm afraid.
Could you by any chance share the slides? There are so many interesting references that you cited in the slides, and I would love to look into.
Yeah, sure, I can do that. Also, I don't know if you've seen it. So after the last slide, there are some slides with proper references. So yeah, sure, I can give them to.
Thank you very much.
Yeah.
Can you say something how the situation changes when you add exponential functions?
Yeah, the problem with exponential functions is that they are just not in this nice theory of the real. So in this algebraic techniques like Gribner basis, CAD, virtual substitutions, they just cannot do anything with it. And so what you do is you do this linearization technique, and then whatever remains after that hand over to CAD, and it's just not very good to it with it. So if the exponential part of your problem is really easy and essentially it's just a bit of rewriting, then it's okay, it can deal with that. But if you have a problem that is actually interesting in the exponential functions themselves, then most likely we will either time out because we continue linearizing stuff that is completely irrelevant, or we will just say unknown because none of the linearization really applies. I mean, give it a try, maybe you are lucky. But most likely, like the simplifiers in Maple or the likes is much more powerful for such things. So maybe the motivation for including that it's usually that that it is sufficient to kind of approximate what the exponential function does. So think of you are talking about like a hybrid system where you just need to roughly approximate how the system behaves over time. Then this may be sufficient. But yeah, then you might already get away with just using a simple linear approximation in the first place.
More questions? Yeah, so I have a question regarding what goes into CVC5. That's you said the solver that you have been involved with in the past years. So you already mentioned, so on the SAT side, there's basically it's some version of MiniSat that's doing the work. So how about the the linear solver? Are you using something from a library there, or is this implemented from scratch in CVC5?
So most of the high level algorithms are all implemented from scratch. And the reason there is, of course, we have an optional integration of GLPK. The problem is that here, you can actually kind of see it on the slide for the series solver in the answered case. So that's one example. You need this subset of constraints that is already unsatisfiable. And it's not really difficult to do that with simplex, but you need a bit of bookkeeping to answer that question easily. And all the off-the-shelf linear solvers just don't do that. And this integration of GLPK, there's a lot of custom patchers, and it's a pain to maintain. And at the same time, if you use CVC5 on just a set of linear constraints, you're probably better off with a standard linear programming tool, whether you skip GLPK, whatever. But the crux is this combination with a SAT solver, and thus it's fairly difficult, but not like not super difficult to come up with a simplex solver that is sufficiently efficient, that will not be able to compete with Groby or anything, but it's sufficiently efficient for this use case. And thus,
because overall your number of variables that you need is so small that you don't need a high performance LP solver. Yeah.
So if we have 1 million of real variables, then we may get to a point where like skip could deal with that and our linear solver cannot. But then most likely we would already get stuck in this whole interaction between SAT solver and series solver. So that's also something. If you don't have Boolean structure, then if you have a dedicated solving tool for that, like a linear solver, then use that one. most likely you are better off with that. Yeah, what we use is, and I think all the SMT solvers use that, is GMP for the number representation. So we are not going that far. But yeah, all the series solvers, the core algorithms of the series solvers are all custom implementations. But you mentioned also for mod scheme as a technique that you need. That's also for the linear quantifier elimination, right? Yeah. So do you ever do like non-linear Fourier mod scheme, like direct elimination of variables? So in my PhD I worked on SMT-RED, and there we have. So I'm not exactly sure what exactly you mean by nonlinear Fourier mod scheme, but what we did there was we extended it so that if only the variable we eliminated was linear and everything else could be nonlinear, so that's what we considered nonlinear Fourier mod scheme. We use that there for special case. Sure. Yeah, but also there is a problem. I'm not sure whether there are libraries that do that. I mean, it's fairly easy, so I'm not sure it's worth doing a library for that. But even there, you need all this, again, tracking of what were the constraints that made it become unsatisfiable. And yeah, even there, it's all custom implementation, unfortunately. We would really love to use an off-the-shelf solver for that. So I really don't fancy implementing CAD myself. But I mean CAD. So in Sage, for example, we have QEP CAD, but it's highly problematic. It's not very stable. It has all of these issues with memory management, where it just crashes. So on the other hand, we do have very robust, polyhedral computation solvers. So. And so, for example, something on the level of the Parma polyhedral library, PPL, they are like providing polyhedral representation conversion is what you have in CVC5. Is it competitive with that kind of level? Do you know? I don't think we have something really equivalent. So because for once. PPL works on double representations, right? No, it's rational. It's rational. Yeah. Yeah, but so we don't really work with these in the geometric sense. So if we have linear problems, we do simplex, and that's it mostly. Sure, but in CVC5 you can do the explicit quantifier elimination as well. Yeah, so you can obtain the projected systems or not. I'm not sure. I've never looked at the code, and it's kind of separate from the rest of the solver. This getQE query. To my understanding, it uses comparably naive Fourier mod scheme, gives you the resulting formula, and that's it. But I'm not entirely sure, I must admit. We have another nice system in Sage. It's called Normalis. It has a very sophisticated double description method, so for polyhedral computation, and this one is under active development, and so basically if you need this kind of additional information like infeasibility certificates and stuff like this, I'm pretty sure that the developers will be responsive to yeah, that could be interesting. So because so there's a lot of tuning that has gone into these methods. Yeah, so Fourier mod scheme can be written down in both on the primal side and the dual side, and so in some sense it's equivalent to the beneath beyond method of polyhedral computation, and so a lot of tuning has gone into the details of these algorithms to avoid explosion with Yeah. Maybe a last comment. So because in the talk before it was mentioned that you think about using SMT solvers. So all of the solvers from my last slide from this table, all of them are freely available, and all but MassSat are open source, and they are all comparably easy to build. So it's like you clone the repository, you run make, and you get a binary. So just download them, try them out. They have a common input language called SMPlib, so it's fairly well documented how the input works. So yeah, and if you have any questions, just feel free to ask me, or I'm pretty sure any of the developer teams will be happy to help.
Sounds good. Do we have more questions? Otherwise, that's kind of like a nice closing word. So let's thank Gereon again. And I would suggest that we take a 3-minute break, and after that we can continue with open discussion of symbolics. Now. Okay, welcome back, everyone. So there's no program, but I suppose we can collect some ideas of what would be interesting to discuss. So anyone, please feel free to speak up.
So I mean, just from my own perspective, I'm interested in knowing why in discussing with people where we can collaborate between SymPy and Sage and FLINT and so on.
Yeah, I was hoping very much that so this Symbolics forum here can kind of create the spark to do more in this direction. I think an obvious thing has been mentioned already, kind of shared effort to build rather complete FLINT and R and so on interface for Python. So low level enough that it can be shared between the various systems. So should it be Python for ease of maintainability, and hopefully that would reduce the maintenance burden on all sides. What was mentioned before, that going through Julia might be a route. It's probably less preferable for Sage, as has been mentioned.
I mean, that wouldn't be considered an option from SymPy's perspective. So
yeah, I mean, it would be a very heavyweight dependency on a kind of a runtime availability of liblllvm at least, and then at least some stripped down version of Julia. I don't think that's and frankly, I have doubts about the long-term viability of Julia, I'm afraid to say. So I've been following Julia for a long time, because I think so. I used to do Lisp professionally for about a decade, and so I was really excited when the Lispers in disguise invented Julia and so on. But it unfortunately hasn't kind of picked up enough, let's say, corporate buy-in, and so I'm quite skeptical about its long-term perspective. I mean, now other languages that kind of use, sorry, my video is lagging again. Other languages that kind of have picked up the modern approach, such as Rust, have surfaced, that have many of like the modern semantics of modern languages, and so I've resisted picking up Julia because for once I wanted to be on the mainstream side of things after spending many years on this, so I think it would be tricky to invest so much work in going through the Julia route. Could easily be a dead end.
That's interesting. I haven't heard anyone else express that view about Julia yet. It still seems quite young to me. I know there are various colleagues of mine who are very enthusiastic about it.
I was enthusiastic too, but also cautious because I didn't want to kind of repeat, wasting years on stuff that goes into in the end obscure language. I mean, that's Julia has been enormously successful, but it seems to me that it is in some niche of the sciences is replacing kind of MATLAB as as a language for quick experimentation and also for for running experiments, but without kind of the corporate buy-in that there's basically no really visible shops that are funding Julia development. And it's very much in contrast to Python, to Rust, to .NET. So anyway, just my opinion. That's why I'm cautious about Julia, and so for sure for Sage, it's at least not a short term. It would be nice to have interoperability to avoid. Kind of reinventing the wheel on like high level facilities, but for things that where one needs a really tight kind of low level integration, such as fast polynomials and so on. I don't think we would want to go through the extra hop of marshalling and stuff via Julia. So.
So regarding Python FLINT, or FLINT in general, so I wonder if maybe someone could summarize like what exactly is the situation with Python wrappers? Because I think Fredrik mentioned there was like wrappers in Sage. So are the Sage wrappers like more built out than Python FLINT? Is it just a question of backporting that, or is there? I think you're muted if you're talking, Fredrik. Or I can't hear you.
He's coming back. Yeah, situation in Sage is that William just posted the link. We basically only have stuff that was already in FLINT 10 years ago. So basically all the good new things from the FLINT 2 series, with a few exceptions, are basically not wrapped. And so basically, I suppose one could just start from scratch to some extent. And so I do agree with what Fredrik suggested, that kind of going through this generic interface where you have a kind of a parent pointer, parent and element there. That does sound like a kind of a convenient interface. I think going through that extra pointer interaction, I think is quite appropriate if one's going through interpreted language to C++, the function call layer anyway. So nothing is lost there. So
can you hear me now?
Yes.
Yeah.
Okay, great. So yeah, I missed what you were saying, or the start of what you were saying.
So, the question from Aaron was to kind of summarize what's the status with FLINT wrappers for Python, and Matthias told us a little bit about the Sage wrapper.
Yeah, Python FLINT is more complete. The Sage wrapper, I think it does some of the polynomial types and matrix types in FLINT. and some of the ARB types. It doesn't do multivariate polynomials.
That's right.
It doesn't do some of the ARB types like ARB polynomials and ARB matrices. I don't remember exactly which ones. But Python Flint also is far from complete.
So is the plan to just try to complete it? Is there a plan to try to do some automatic wrapping so it stays in parity, or?
Automatic wrapping could also be interesting. I don't know exactly how you would do that. The Flint...
I've had a quick look at automatic wrapping for this, and I haven't found anything that can do it. I mean, there are various libraries that do have some automatic wrapping, but they have their own bespoke solutions. There isn't a generic library that does this. Sorry, Fredrik.
Yeah, there is actually an ARB interface in Julia. What is its name? arblib.jl, I think. And they basically parse the documentation of ARB for all the function signatures, and then generate Julia wrappers automatically from that. But it's a bit of a more low-level interface. So I don't know exactly what kind of restrictions you have, but it might not provide all the conveniences that you need in the Sage wrapper, or that you might want in Python Flint.
I think from SymPy's perspective, having a wrapper for, say, Flint that literally just exposes all the Flint functions in a very raw form would actually be very useful. And if that was easier to maintain, that would be more useful than something that would lag behind Flint development.
Have you tried CPPYY? So I wrote a CPPYY wrapper for ARB, at least ARB and ARF, so not the entire ARB library. So that worked pretty well. So basically, I wrote a C++ wrapper for ARB, and then took that C++ wrapper, and it automatically gives you a Python wrapper.
Do you want to show that a little bit?
Give me a second. keep going while I bring this up.
Typically, what you would see in at least what I've seen in many Python libraries that wrap C libraries is you have a low-level layer that's sort of just a one-to-one mapping of the C function API, and then on top of that, you would build some conveniences in Python or maybe in Python if that's necessary. So if you need to go down to the low level to do something directly in ARB, you can do that, but you also have higher level API, which probably consists of things that don't make sense in Flint itself, but only would exist in Python Flint.
But I think the main thing, so from SymPy's perspective, the cost of calling into this interface is extremely small compared to everything else. So in a context where SymPy would use Flint to do something, so much more other stuff goes on before SymPy actually calls into Flint, that really it doesn't matter whether there's a little bit of Python code that connects things together when we get to the Flint level. I mean, does that make sense?
Yeah, well, for something like solving a linear system, I mean, it's a bit different if you want to use, let's say, Flint rational numbers, and then do things in Python using those numbers. Then you might have to worry a bit about the overheads.
No, absolutely, yeah. And so, and obviously, if SymPy was to use Flint, then we would want to do that. So we want to have that in place of GMPY2.
Yeah, so I think like for rational numbers, you would have just a low-level interface that just calls the C functions, and then you would build a Python class on top of that that has the, that provides a user-friendly API. And that Python class could be written in Python if it improves the performance significantly.
Yeah. So Python Flint already has this. So it already has rationals and integers and univariate polynomials. I'm not sure if the multivariate polynomials are available yet.
I don't think so.
I don't think they are, because that was the number one thing that I wanted.
Yeah.
So you mentioned in your talk, Fredrik, that you pretty much make everything public in Flint. So does that mean that the API is very stable, or are there API breaks between versions?
Well, in practice, you have functions that are more likely to be used by the public, and functions that are only likely to be used by developers. And we try not to break the commonly used functions very often. So it's reasonably stable. We sometimes have small breakages between versions, but it's mostly stable.
But when the breakages do happen, it's a compiler error rather than a different result.
Usually, yeah, there have been some exceptions, but in those cases, we try to make this really clear in the release announcements. And there have been not too many of those instances.
So something I mentioned in the talk earlier was about the idea of sharing benchmarks and test suites between different projects. Is that something that anyone is actually interested in?
I would say I'm interested in that. And yeah, I guess you can have problems on different levels of abstraction. There are things that you could benchmark, you could use for benchmarking Flint, but then it has to be somewhat low level, like things dealing directly with polynomials. And maybe for SymPy, you're more interested in a bit more high level benchmarks.
We're interested in benchmarks on all levels, I think. But if you can define a problem, like factor a polynomial with integer coefficients.
Yeah, so for example, if we take factoring univariate polynomials over the integers, there is a set of test polynomials that's included in Flint. And I think it's been used kind of as an informal benchmark for not just Flint, but for comparing with Magma and NTL and other implementations. So it's from a few different sources, and it's I think it's a pretty good test suite.
Yeah. So that's the kind of thing I was talking about. It takes a lot of work to make something like that, and it would be good to collect things like that together and make them usable from many different environments.
Yeah, the other problem with benchmarks is that if you might have a good test suite for testing broad functionality, but for benchmarks, you want to have something that is going to basically going to test performance. So you want to have things in there that are likely to catch, odd performance corner cases and things like that.
There's a cool Python library called airspeed velocity that I've never used, but I've seen its output, and it's designed for benchmarking Python packages over time. I don't know if you guys are using that, but it could be helpful.
It's good airspeed velocity, and SymPy, we do use airspeed velocity. In fact, and so every pull request, those our benchmarks will run in airspeed velocity on CI, and it will compare the performance between the master branch and the PR. But well, there are several problems. So one of the most major problems actually for SymPy is caching. So because SymPy caches things, a second run of the exact same operation runs much quicker than the original run of that operation. And airspeed velocity, much like many other things, I think it runs these things in a loop. So it repeatedly calculates the same operation and then reports the minimum time that it takes to run, or the minimum average over something, something like that. And so as a result, it actually disregards the original time that it took to compute the thing. So airspeed velocity, but also actually the major problem of airspeed velocity is that it makes it quite easy to do things like run all your benchmarks over all the Git commits over a period of time, but it makes it quite hard to just run the benchmarks. So you want to say, I just want to run that benchmark. I've changed the code, I've made it faster. Please rerun that benchmark for me. It's actually surprisingly awkward to do that simple thing.
Yeah, it's designed to find performance regressions. So if you run it, you have a benchmarks week and you run it, and you'll run it like overnight or over the course of a few days, and it'll run like every commit in your history, and you'll get these nice graphs, and you can see, oh, it's spiked up here. What's this commit where it's spiked up at? It's not really designed for other things that you might want to do with benchmarks. So, it's really hard to use it to like compare benchmarks across different projects or something like that. Or even like Oscar said, it's hard to just sort of run the benchmarks like in development to sort of use them as a guide to performance improvements. So if anyone else is familiar with any other tools that are sort of designed around running benchmarks or producing nice output from benchmarks, or even just sort of like taking care of things like making sure that benchmarks are run uniformly and the statistics are good, please let us know, because I think that's something that would be very useful as well.
Yeah, so we've been running airspeed velocity benchmarks just in GitHub Actions, and there's of course a lot of noise, but somehow you do get.
Yeah, well, running benchmarks on CI is a whole other problem.
Yeah, but somehow you see the regressions when they happen. I mean, you have a ton of noise, and then you don't know exactly where the regression happens, but you do see it if you do it with every commit.
Right, but yeah, so I think finding regressions is actually sort of one of the things that's easier to do with the existing tooling. But the hard thing is sort of improving performance from where you are right now and taking that down and using benchmarks as sort of a metric for that. So making it easy to just, change some code and then run the benchmarks and see what's still slow or what's improved. Or even just also comparing against like different projects to sort of see like what a good baseline is, what you should be aiming for.
Have you guys looked at whether you could somehow globally disable the caching that SymPy is doing?
Oh yeah, we can do that. It makes it extremely slow.
Oh, I see.
So the problem is it happens at different levels of the computation. So a single computation might have different parts of it that are cached, and that caching is something that is maybe sort of relevant for the performance of the final output. But if the final output itself is cached, then it's not very meaningful to run that again.
what you need is something that empties all caches globally, but maybe your caching isn't set up to support that.
No, our
there
cache supports it. I think the problem is airspeed velocity doesn't have good support for doing that.
Yeah, so there are different levels of caches. So some caches are caches on the objects, and some are part of a big kind of global cache. And you can clear the big global cache, not the caches on the objects. And well, yeah. Anyway, it's a very hard problem measuring the performance of things that involve caching, basically, because it's hard to even define what should be the right answer.
Yeah, for example, we have a cache, like a rational number cache, where it'll cache basically because whenever you create a rational number, it will cancel out the GCD, so that's cached. And obviously, if you have the same rational number appearing multiple times in a calculation, that's going to improve the performance of it. That's a very low level cache.
Are your caches thread safe?
I think that's also another problem that.
Yeah, this problem is can probably be solved using the same thing, basically by making keying all caches to kind of a cache state that's can be managed explicitly, and that's a way to actually make things decouple the threads from each other.
So the caches are thread safe, provided you don't alter a certain number of global variables. So that there are some global variables that affect the things that would be computed that then become cached. And when you change those global variables, the cache gets cleared. But I don't think the clearing of the cache itself is thread safe.
So the new assumption system in SymPy, is there, if I remember correctly, this is purely functional, right? So you don't have like a global state. I mean, so the problem with the old assumption system is, right, it's key to symbols, and symbols are super global, right?
Well, sort of yes and no. So symbols themselves are not global. In fact, if you create a symbol, like if you create one symbol X with no assumptions and you create another symbol X that's say positive, those will be considered distinct things, and only the expressions that you create with the positive version of it will be positive. So that in that sense, the old assumptions is all doesn't have any global state.
Okay. So symbols are not unified by name somehow. No,
they're equal by name and by assumptions. So so that the assumptions are stored on the symbol object itself. And actually, the new assumptions, there is actually a way to define a global assumption, which personally think is not necessarily a good idea, but there's also like you can have like a context manager where you like set an assumption inside of a block.
Yeah, I'm kind of wary of context manager for these things because it kind of precludes concurrency. Yeah. Yeah,
it's also a very clumsy API as well. I mean, this is sort of like stuff that was sort of added as sort of like experimental like things, but I think it's not really a good idea.
Yeah, so what I would like to see for Sage is basically an kind of purely functional assumption system where I can make truly local assumptions that are not keyed to let's say dynamic scope, right? So like Python's with blocks are, but that I can really manipulate, that are efficient in the sense that I can push something on top, and I don't have to make a copy of all the other assumptions and so on. So that one can, and then there would be like cached copies of these things with handles in the various backends that we use. It could be and the SymPy new assumptions version of our assumptions, and there would be a maxima context that represents these things. And if we do CVC5, then and everything happens to be polynomials, then there would be a representation of that in terms of CVC5 inequalities and so on. But for that, it's really crucial that one really has this clean functional representations, or not mutable states. That is kind of what the situation is right now in Sage.
Yeah, so we've tried thinking about the best way to do this. Like, should we like add an assumptions flag to every function so that things get passed around, or should we have some sort of a context manager? I don't know if we've yet figured out the correct way to do it.
Fredrik, in your code, what do you do with stuff like this? Do you have?
I've tried doing it a few different things, and I'm not sure if I have a complete answer. I lean towards saying that doing things in a pure functional way, it's going to work out much better in the end. I mean, you can have a context of some kind where you can stick a lot of data inside, like assumptions and other things as well. But then I think at a low level in your code, you might want to be able to pass that context around explicitly, even if it's a little bit inconvenient.
Yeah. Well, I guess the old assumptions in SymPy are more or less functional, because the assumptions are, they're part of the symbol object, and everything is just computed from that. The problem is, of course, you can't represent assumptions on anything except for symbols.
There are other problems as well. So in SymPy, there are loads of places that replace all the symbols in an expression. So rebuild the expression with different symbols in order to have different assumptions, and then replace them back again later. And it's, that's completely unnecessary if the assumptions were held outside of the symbols. So what's the goal from Sage's perspective? So Matthias, you asked about assumptions on the SymPy mailing list.
I mean, so what we have in Sage is just wildly inadequate. So first of all, assumptions are not really synchronized between the various backends that we use. Yeah, so Giac and Pynac and SymPy and Maxima. So it's quite contradictory and ad hoc what's happening there. So basically, I was trying to shop around for something solid. I really liked the thing with the q dot something in SymPy. I haven't really looked much into it. I thought I got the impression that it's a little bit abandonware, but it's still the design I found appealing. So that you basically keep these things in the form of expressions and so on, and it mostly looks functional in this way. It inherits that from the fact that your expressions are immutable, and so this is all nice. The problem is that our Sage SymPy interface is not as disciplined as SymPy itself. So, for example, when a variable tells us it is x, we don't care about what assumptions are attached to that thing. So basically, the round the round tripping is very heuristic in Sage. Things, Sage involves a lot of wishful thinking about, what is equal to what. So lots of things coerce just in a very friendly way. And so I think assumptions could easily be lost when you basically reconstruct the SymPy variable object from its name. I'm pretty sure that there are bugs there.
But what's the interest? Is the interest in thinking about how to design a new assumption system in Sage, or thinking how to? Okay.
So so I would be happy basically if you tell me that you are happy with the SymPy new assumption system and don't consider it as a kind of like a dead end. Then based on the impression that I had from reading the code, I thought it's at least a great starting point. So the one tiny concern that is on the Sage side is that SymPy does have a startup time that's kind of on the order of maybe 2 seconds or so. That makes it tricky to. Might be wrong about this, but that makes it tricky to load up by default in Sage.
2 seconds seems like longer than.
Yeah, I just timed it. It was a bit less.
Less, yeah.
But
Okay.
so this would be like a one-time, like you're actually interfacing for Python. You're not like loading it up in the subprocess every time, right?
Yeah. So sure. No, I mean, so the issue is just that Sage already has a pretty long startup time, and so we wouldn't want to just load it up eagerly as part of our startup, and it would also be inconvenient if we loaded it up in the very moment that anyone types X as the first thing in our Sage prompt. Yeah, so that's, I guess. I mean, this is just a tiny thing, but
that makes sense. But I can understand Sage wants to have its own assumption system anyway, regardless of that. But so the question is, do we think that the new assumptions are a good design to emulate and follow? I guess.
Yeah, I guess that's the question. Is this good enough for basically your long-term purposes? Or should we somehow invest in a discussion of, what would be a design that is kind of, good enough for various systems, both for like, I mean, so there are various communities that need these kinds of assumptions. Something that hasn't been mentioned today, but was a topic yesterday were, optimization solvers. So optimization solvers also have like, you can see that feasible region of optimization problem is just a large scale system of assumptions, whether it be linear equations, inequalities, or nonlinear ones. And so global optimization systems also have need these large scale representations of let's say symbolic assumptions and then particular types of reasoning about it. And on the other hand, of course, also optimization methods do provide some kind of calculus for reasoning about it. So like Gereon, I think is no longer in the chat. So when you said they have these bound tightening procedures, bound propagation or interval propagation things, these are all widely used techniques in global optimization as well. So there are multiple involved communities with different kind of I suppose domains and generality of these constraints that one can consider. And the question is also to find something that is actionable.
Sorry, go on, Fredrik.
Yeah, so I've kind of been favoring an approach for symbolics for a while, where you keep symbolic expressions as a very simple, kind of mostly syntactical data type that doesn't really need to know a lot about computation. And the idea is that you should be able to construct and manipulate expressions and pass them between systems without having to load a lot of computational stuff. Like if you want to create the assumption that x is positive, you should just be able to create an expression x is positive, and you should not have to load the assumption system of the engine for simplifying assumptions that SymPy uses. And then when you have a kind of representation of symbolic expressions like that, then you can have multiple backends that can just traverse and manipulate or convert to different formats internally. And you can have simple things that are quick to load and try to deal with simple cases very quickly. And then when you really need it, you load some more heavy machinery like Kremer basis and symbolic cylindrical algebraic decomposition and SMT and SAT solvers, everything like that. So it's kind of design I've been exploring a bit, doing some. So I was working on a kind of simple symbolic expression engine for Fungrim. And without actually having a proper computer algebra system behind it, just doing some pretty simple manipulations, I thought what I ended up with was a quite comfortable to work with, because the symbolic expressions themselves felt very lightweight and intuitive.
Is it reference counted? Can you share?
So that I did just in Python. I also worked a bit on a C implementation. It's not exactly the same thing, but the idea there is also that you have a simple symbolic expression type, and then you can evaluate it to transform it using different backends. So for example, if you want to check some identity involving real numbers, you could first try interval arithmetic to check if it's false. And if that fails, so you really need to prove that it's exact, then you can try actually an algebraic computation, which will typically be a bit more expensive. So I think, you know, one of the design flaws of SymPy right now is that it rewrites expressions automatically. And I don't know what Sage Symbolics does right now exactly, but in general, I think it's better to have symbolic expressions that are inert by default, do no simplification, so then the user can transform them in different ways.
No, I agree with that. I agree. So,
oh, go ahead, Oscar. I said I also agree.
Yeah, I see.
It's the problem is it's hard to remove automatic evaluation once you have it, which is one of the reasons why it's good to not have it, actually. Because if you decide you don't want it, it's hard to get rid of it.
Yeah, no, I completely agree. One of the things I want to look at over the next year is building a different symbolic model for SymPy, and this is something. So I know Matthias asked about SymEngine as well, actually, which we didn't talk about. So SymEngine was an attempt to make SymPy is an attempt to make SymPy faster by re-implementing part of it in C++. But from my perspective, it's the wrong approach. It's not the way that I want things to go. So it's taking all of the things that I think are not good about SymPy's symbolic model, like the automatic evaluation that Fredrik was just referring to, and baking those into C++ so that it becomes very hard to change them in future. So I would like to make a new symbolic model, something that can be much more efficient in pure Python, and then also be made faster using something, you know, like C or Rust or something else.
So to answer a question that was asked earlier about what we think about SymPy's new assumptions system, it's hard to say in terms of like actually using it in library code, because right now very, very little library code actually does use the new assumptions. And maybe that's a sign that it's difficult to use, but it's also a sign that just not much is implemented yet. I will say I've sort of come to the conclusion that the quote unquote old assumption system that I talked about it's not something that's actually bad. I think it's actually very convenient for the majority of use cases. You just define assumptions on symbols, which is usually what you want to do. And they sort of follow the symbols around in a sort of functional, immutable way. And it's very easy to query assumptions as long as you're doing something that it supports. I think it works pretty well. Like I said, it's a little clumsy to use it in the actual handlers and some of the more advanced things because of the 3-valued logic. And I think it was probably a bad decision to use Python's none type for 3-valued logic. I would avoid using that. I would create a custom unknown object that refuses to evaluate to a Boolean value. But I think the new assumptions, the sort of functional storing things separately is just it's a little harder to use as an end user. So it's something you only want to really use if that's the only way that you can express what you're trying to express. But it is nice on the other hand, having it be those are basically just like first-class symbolic expressions of Boolean predicates. And if you want to represent something like x is greater than 1, you would just create the inequality object to represent x is greater than 1. And if you want to, represent some Boolean operation, you just combine them using the and and or objects, and that it makes it very clean to do, especially if you're familiar with predicate logic, to sort of represent things using just standard Boolean algebra instead of trying to fiddle around with 3-valued logic or whatever. And having that as a symbolic representation does open up a lot of possibilities of things you can compute, which are impossible if it's like in Python code. So I don't know if that answers your question. It's kind of hard to answer if the new assumptions is something we like or not, because it's not really used yet.
Yeah, so let me follow up a little bit. So suppose okay, so let's see. Things are keyed to symbols. Yeah, so right now it's just an element. It's just a slot in the symbol object, right? These various assumptions, and but you can think of it as there's global state that contains a mapping from symbols as objects to those assumptions, right?
You could think of it as global state. I mean, it's attached to the symbol object. So
that's a trivial semantic transformation. Yeah,
I mean, I guess any functional system can be thought of as the global state of the entire system, but it's not. There's no like mutation of state or anything that happens like that, or like any of the other weirdness that you can get with global state. So yes, I'm not sure I would say that.
Let me continue the train of thought. So what now if one backed basically the methods that query the old assumptions by something that is actually represented by new assumptions. So suppose a patch like this came along that keeps the same interface, but does away with actually storing this kind of information in the symbol objects, and instead backs it by new assumption objects.
I mean, that's what happens now if you use the new assumption system. So you can use it. It will combine the information from both systems.
Yeah, but the other direction is not implemented. And the other direction is not clear how that works because the assumptions are separate from the symbol. So if you say is X positive, like what do you really mean there? Is there like a Q dot positive object somewhere floating around that indicates that it's positive in this context?
That's why I'm saying being attached to the symbol is the same thing semantically as being in the global state. It contains the mapping from.
I see what you mean. Yeah.
Yeah. So it's not really, it's just a technical distinction whether it lives in the slot or whether it lives in the mapping from the global, list.
Right. I mean, I guess the only difference is you can have the same symbol name with different assumptions, basically. So there's not a limitation there. But sure, yeah, I see what you're saying, and yeah, that's sort of the question of how these two different models of whether it's stored on the symbol or stored separately has sort of made it hard for us to adopt the new assumptions because it's not really clear if we separate that. All the code that's written now that uses assumptions is sort of working on the assumption that it's built into the symbols and built into the expressions. So how do we actually pass assumptions around if they're separate? Do we have some sort of a context? Do we just have like another flag that we pass things through? Do we, I don't know, like it's something that we've discussed, but ideally you want something that isn't too cumbersome for common use cases either, because you don't have to type a bunch of extra stuff just to assume that something's positive all the time.
Yeah, but that's where we've not agreed what it should be, right? So what we've not agreed is what should be the public interface for doing this. So what is it that users are supposed to do? So are they supposed to call the solve function and then say assumptions equals and pass in their assumptions? Or are they supposed to set global assumptions? Or are they supposed to, that's the stuff that's not agreed. If that was agreed, it would make sense. You can just pass the assumptions as an object, you pass it around, you call ask with it. The other side, which is difficult, is the way that the old assumptions are built into evaluation. And in that evaluation context, there's no way to pass anything in. So you would have to rewrite so many functions to be able to pass anything into those.
Well, ideally we want to just remove assumptions from evaluation, like Fredrik was saying, but that's a challenge. Removing any evaluation is hard, like I was saying.
Yeah, but the difficulty there is that the old assumptions does more than what you would think of as assumptions. So you can use the old assumptions to ask a query of an expression that doesn't involve any symbols. So if I have something like 1 plus root 2, that system will tell me that it's not equal to 0. And that's the difficulty there. So we can't separate those.
So to me, it seems clear that one needs both a low-level interface and a high-level interface. Low-level, purely functional with basically context passed. Yeah, so that's kind of critical if you ever want to extend things to being thread safe, for example. And on the other hand, users at the interactive top level or something, users need a notion of a global state. Yeah, so otherwise it just becomes too cumbersome to say and I mean so there is of course, yeah, so there's potential in kind of tying kind of the current let's say current dynamic assumptions to the control flow. Yeah, that's always tempting. Yeah, but this should only be a convenience. Yeah, so if you build things at the low level using such things, that's just that leads to trouble. Yeah, but I don't think there's any fundamental distinction really right now between your old and your new system. Yeah, just because something lives in a slot doesn't mean that it's any less local or global.
Yeah, well, it is now because there's no way to pass in the new assumptions to virtually every function. So it's nothing knows about them.
Yeah.
But I will say, just as a final answer to your question, I think I do really like the new assumptions when it comes to sort of defining like the actual predicates that should be used to do deduction, like that example I showed in my slides, where you have like a predicate on the power object that's just like this predicate thing. You end up with these basically one-liners of things that would be like these huge blocks of if statements, and if you were to do them in Python, and it's very nice to have that just be sort of written out as expressions. So I would definitely recommend trying to do something like that. I think there was some update on the FLINT stuff.
Julian has something to show, yeah?
Yeah. Can I share screen here? It seems so.
Go for it.
Yeah, so I'm not sure if you guys have seen CPPYY before. So basically it's I think it was originally PyRoot, but I'm not sure about the history exactly. But it seems to understand FLINT. Oh, does not. Is that what FLINT is called? No, FLINT. Yeah. So you give it a header and you tell it where the stuff is actually defined. And so now the only glue you need, I think, is that you have to do something about this weird FMPZ_T, which it doesn't understand. So you need to turn this into something that is a bit more C++-like.
Void star.
Yeah, that would be maybe something, but that does it. Right, there was something here. Okay, and now you can create one of these. And now you should be able to call FLINT methods.
Oh, I'm sure you want to initialize it before you actually use it.
Yeah, I should have done that, but it still works. Yeah, good point. Good point. I guess once I leave the whatever it is, the small values, then I'm in trouble. Yeah, but you get the idea.
So is this CPPYY? Is it like what is its dependencies? It's not.
So the dependency is Clang.
Is this would this be like a runtime dependency of the library if you're using?
Yeah, so we're it's a very heavy dependency. I mean,
but it is the idea that you could use this to automatically generate the wrapper, or?
I mean, yeah, the code you need is this to generate a wrapper. Then this will leak memory at the moment, so you need a destructor in here to make. Like you would need a constructor that's the FMPZ init that I forgot, and you need a destructor that's the FMPZ clear, and then you get reference counting on this thing.
But it's not actually generating like a wrapper. This is just like a runtime, sort of like a C-types kind of thing, right? Am I understanding this correctly?
I mean, yeah, it compiles code.
Does this bring like a copy of LLVM with it or something?
If you pip install it, then yes. Yeah. So the pip wheel is very heavy and contains all kinds of stuff. So it's essentially, I mean, if you know Cling, it's very similar to Cling.
So it uses lib LLVM, yeah. So
yeah, exactly.
Python binding to lib LLVM.
Yeah, and it generates code at runtime for these things, and
there's no way to make it generate that code statically. So it's not a runtime dependency.
I don't think so. I mean, yeah, I don't think so. No. I mean, it has there's some pre-processing tool. I'm not sure what that does actually. I've never tried. So I'm using this in several projects, and it works pretty well. It sometimes has trouble with very crazy C++ stuff. So if you go very deep into Boost, for example, then things tend to break. But that's, of course, not what we're trying to do here.
So I was just going to say it's getting quite late here, so I'm gonna nip out. But very nice to meet some of you, and very nice to see some of you again. Right.
Bye.
Bye. Yeah, the same for me in a few minutes, probably.
Maybe it's just getting late in many parts of the world. Kind of late in California already. So maybe we close the session, but form the plan to stay in touch about symbolics issues. I think there's a lot of shared concerns and potential for collaboration. So thanks all for coming and for staying and sharing.
Yeah, thanks for organizing this.
Yeah, thanks. Thanks for inviting me to speak.